papare sa muna 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 keke, sa muna 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 keke. Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium merah pipinya. Kampungan jauh di mata, kunwangsan sebaku liliang, takkan aja kawan-kawan nalamu, sangke basuh yang surya.
Indonesia dengan ini menyatakan kemerdekaan Indonesia. Hal-hal yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science. Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Hello, good morning, afternoon, or even evening to all the participants who is tuning in from all the places. So welcome to the last day of the ICTP workshop on classical and quantum machine learning for condensed matter physics. So for the last day of the workshops, we have one keynote presentation and 3 contributed talks. We also have hands-on session in the afternoons after the breaks. Last but not least, we will have closing statement after the hands session concludes. So my name is Gagus. I'm researcher at the Research Center for Quantum Physics, National Research and Innovation Agency of Indonesia, and I will be your host for the keynote sessions today. For the last day of the workshop, we have one keynote presentation today. So today we are going to hear a presentation by Dr. Cica Giustiani about variational quantum algorithm. And this talk will provide an overview of variational quantum algorithm and their potential for near-term quantum computing applications, particularly in chemistry and also condensed matter physics. So it's my pleasure to welcoming Dr. Cica Justiani. Hello, Cica.
Hello.
How are you today?
Great. You?
So you can, I'm good also. So you can start sharing your screen first.
I thought I have started already.
Oh, okay, thank you so much. And please be informed to all the participants. So if you have any questions during presentations, please post your questions in the chat. After the presentation has finished, if you would like to ask question directly, please raise your hand or request permission in the chat. After which we will enable to you to unmute. So for Cica, please feel free to ignore any question that appear in the chat during your presentations. We will address them in the question and answer sessions. So before we kick it off, please allow me to briefly introduce our speaker today. Cica received his master's in simulation science from RWTH Aachen University, Germany in 2015. And she then earned his PhD in physics from the same university in 2020. Following this, she conducted postdoctoral research at the University of Oxford, UK, from 2020 to 2023. Since then, she has been working as a consultant at Quantum Motion in London, UK. And beginning in 2024, she also served as a postdoctoral researcher at the University of Sorbonne, Paris, France. So with that, Cica, are you ready for your presentation?
Yes. Should I start
If,
the
yes,
sharing?
if so, the stage is yours.
Okay. Thank you, Gagus. I hope it is working now. Okay. How is it? Is it working? Okay, good.
Yes, good. Go ahead.
Everyone, thank you very much. It's nice to be here. So today I will talk about variational algorithms and also in the implementations of the quantum machine learning, because the topic of this workshop is quantum machine learning. Okay, so variational quantum algorithms, it's a family of algorithms and it has a lot of applications. So as you can see here, there are like plenty of those. And then today I will talk about several applications. So start from the finding the ground state, dynamical simulations, and then compilations, and also machine learning. So all of these topics, they are connected, related to some chemistry applications, condensed matter basically, and also the machine learning. Okay, let's start from the simulating quantum system. So when someone says simulating quantum system on quantum computer, what does actually mean? So it actually means two things. It either means like some static simulations or the dynamic simulations. In the static simulations, normally you like to find the ground state energy of a Hamiltonians. So as in this solving the Schrödinger equations. And then in the dynamics simulations, you are basically solving this time evolution operator. So this is just Schrödinger equations, and you want to see what's the times, what's the state after time t. It is basically just you apply. The solution is just exponential of this Hamiltonian. And yeah, so basically you like to implement this unitary. Okay, so how to solve this problems, like for example, if we want to solve the Schrödinger equation, we can just evolve the state. So we prepare a state, for example, psi, and then we evolve according to some Hamiltonian h over a bit of time t. And then this equals to the exponential of the eigenenergy. And then if we can just rewrite this form into e minus I to pi phi. So if you notice that this form, it can be solved by quantum phase estimation. Okay, so the relation just simply look like this. And this phase estimation it's a very beautiful quantum algorithm. So basically, this is the quantum phase estimations, and you have this, you prepare some states, and then this is the, you perform this controlled unitary, and this unitary is basically this what's so-called propagator. So this is the time evolution operator. And then at the final state, you will obtain the superpositions of the eigenstate of unitary U. So this quantum phase estimation will project the state psi into one of the eigenstates of the U with probability C. So you see that, for example, if you'd like to, if you want to find out what is the excited energy, for example, you can just prepare a state psi here close to the excited state, close enough. And then with the high probability, the final state here will be projected into this excited state. And then the final output measurement here, it will be exactly the phase phi here. Okay, so it is really a very cool algorithm. And of course, the precision is growing by the phi here. Basically, you can add more qubit to obtain more digit precisions, and also very affected by the U. So if you notice that, because the final eigenstate would be the final state would be the eigenstate of U. If you don't prepare U very well, if it's noisy, then you wouldn't be projected into the eigenstate of U. So that's why this quantum phase estimation, it works only with the fault tolerant. Okay. So I guess I would repeat some of the stuff before. So what is the NISQ? So we are in this NISQ era. So it's basically noisy intermediate scale quantum computing. It's maybe going for a few more years, hopefully. And this is where we have around 1,000 physical qubits. And then this number of qubits is not good enough to perform fault tolerant, but it is enough to perform certain algorithms. So what kind of algorithms that we are looking for? Those are the algorithms that are noise resilient. And then to overcome this, usually you try to perform algorithms that are within the coherence times of the physical qubit. So you want to have your algorithm as short as possible. And then to make the results better, you can perform classical post-processing, so-called error mitigation. There are a lot of techniques. And starting, okay, let's start from this variational method from the variational quantum eigensolver. So this VQE is very similar to this classical technique, basically, the classic Rayleigh-Ritz method. So it's a very old algorithm from 1900, basically. So in this method, you perform self-consistent calculations. So in this method, it says that the ground state, the ground state energy would be the lowest eigenvalue of the Hamiltonian, basically. So to obtain this ground state energy, you can actually just it's promised that there is no energy lower than the ground state. And then to find this ground state, you can basically perform some test functions. You try arbitrarily many functions, many quantum states, psi t, for example, and then you can pick the lowest expected value, and then this would be your ground state. But to search in the Hilbert space is very painful because it's extremely large. So the technique is you prepare some ansatz. So this is basically just a set of bases. You pick some bases, and then you hope that and you parameterize this basis. So you hope that the ground state can be expressed by the linear combinations of your chosen bases. So in this case, our search narrowed down into searching for these coefficients here instead of the Hilbert space. So here you can perform the minimization with respect to parameter alpha instead of the Hilbert space, this phi here. So that our search space is just in the real space instead of in the Hilbert space. Okay, so then the classical optimization is performed over this parameter space. For instance, it's when the derivative of the energy is equal to 0. Then you know that this is actually the lowest energy. And from here, what is the difference to the VQE is simply just this, basically. So using quantum computer, you can estimate the expected value of the Hamiltonian efficiently. You can just perform measurements, and then this would be your energy. And then here, your ansatz, basically your chosen basis sets, is expressed as a series of unitaries that can be parameterized. And it is natural representation because in practice, you parameterize your quantum gates, for example, by modifying the signals, make it shorter or longer. But then the optimization is still performed classically, basically, over this real parameter space. So it's the same, except that you calculate this expected value by means of the measurements on quantum computer. Okay, so the framework of the VQE, you must see this very often. So basically, you have several blocks here. You have the start by encoding your problems, and then you calculate the expected value on the quantum computer, and then you train your parameters, and then you keep doing it until it converges. So it's basically minimization problems of the expected value of the Hamiltonian over parameter alpha. So now I would like to give you some reasons why VQE has good potentials on NISQ devices. First, the nature of this parameterized unitary, the ansatz. So you can construct the ansatz by a series of unitaries, parameterized unitaries that you can tune it basically physically. And then in this case, most of the time, the Hamiltonian is expressed as a sum of the Paulis. So it's just linear combinations of a Pauli strings. So what does it mean by linearity, basically? By linearity, the total expected value is just the combination of expected value of each Pauli terms. So those are independent, and that's why you can perform this expected value in parallel. And for example, this is how to obtain this expected value of each Hamiltonian term. Here, something called the Hadamard test, basically. So here you prepare your ansatz with parameter alpha, and then you perform Hadamard test just for a single Hamiltonian term. So because of this, you don't have to, you can just calculate the expected value for a single Hamiltonian term, and that's why your circuit remains shallow. And that's suitable for the NISQ, which has a short coherence time. And then again, the classical optimization is performed classically over this parameter space alpha. And then on top of that, for some noise, it can be automatically adjusted by this parameter alpha. I mean, it's not all kind of noise. For sure, it must be some type of unitary noise. Okay. So now I would like to walk you through on each blocks of this framework. So the first block is how to encode our problem and then solve this in this VQE framework. Okay, now I will start to explain this by problem case, which is finding the ground state energy. Okay, first, the problem encoding. So here I would like to, here I have some molecules basically, and then I would like to find the ground state energy of this molecule, of this configuration. And first, as usual, you construct the Hamiltonians of this molecule that consists of the kinetic terms and the interaction terms. So this correlations, the column repulsion terms. And in this VQ encoding, the most common way to encode this problem is using Jordan-Wigner mapping. And this is performed in the second quantization. And notice that, and also one of the reasons it is very straightforward to encode it into the qubit, because in second quantizations, your state is expressed as the occupations numbers. So for example, 0 means unoccupied orbitals and 1 means occupied orbitals, and you can directly translate it into qubits. So unoccupied, you put a state 0, otherwise state 1. And this second quantization is obtained by Hartree-Fock. So just a quick reminder, it is quite a well-known, efficient method. So first, you pick a set of orbitals, 1 electron orbitals via self-consistent field. Like, for example, you can include this s orbitals, or you can p orbitals, however you want to make it accurate. And then after you obtain these orbitals, your basis state will be the Sutter determinants, and then the final state. So when you perform the VQE, then your final result will be, and when you convert it, it will be the linear combinations of those Sutter determinants. Okay. Now, since we have the state in second quantization, then we need also to express our Hamiltonians, this one, into the language of second quantization. So in this second quantization, the operators are annihilations and the creations operators. So we need to express into terms of this. There is like standard method to convert. It's very efficient. So then if we have our states expressed into the qubit, and then our Hamiltonian expressed in this second quantization, then the next we just need to convert these operators into the Pauli terms, basically. So for example, in this creations operator, you can just easily construct like this. So it's just creating, if you have input 0, not occupied, the output will be 1, which is occupied. And this is the annihilations. If you start with the if we start with the occupied state, then the output will be unoccupied. And this Z terms here, basically maintaining the antisymmetry. Then these projectors can easily be expressed as these combinations of Paulis. For instance, this can be expressed as this Pauli, and then this one is the +1. Then we obtain our Hamiltonian as a sum of Pauli terms. And of course, there are other problem encodings in this second quantization. For example, this Brahe-Kitaev and the parity encoding, and they will give you different number of qubits, different precisions, and this is still ongoing research. And of course, you actually may stick to the first quantization. So you can also just stay in this a special configuration electronic space. For example, if you're interested, you can just check in this paper. For example, in these results, they simulate the dynamics of the helium atom in the electronic configuration space. So they actually managed to plot the distributions of the electron in the space. So here they used phase estimation simulation, basically. And then if you're interested, you can just check on the paper. Okay, so we covered this problem encoding, and then now let's cover this training. Okay. And this parameter training, one of the common method is using the steepest gradient descent. So you just calculate the gradient and then pick the steepest opposite direction, basically. And there is another way to train, for example, using this imaginary time evolution or quantum natural gradients. In my experience, it is much faster than the steepest gradient descent. So here, basically, you add additional information, this F inverse. So this F basically known as a Fisher information in the machine learning. So for example, in the results of Ardles, Jones, Endo, they compare the for the FQE, they compare the optimizations using imaginary time evolution on the top and the steepest gradient descent of the small Hamiltonian. Basically, in the case of the imaginary time evolution, for every initial state, initial parameters, convergence was always working. If you can see that every start here, they're all going to the lowest energy. On the other hand, this is the example, they use the steepest gradient descent for some cases here. If you see the red cases here, they actually, they're stuck in the local minima. So there are some cases, for example, here that's imaginary time evolution perform much better. I think is someone doing some oops. Someone doing some whiteboard? Okay. Okay, thank you. I think someone accidentally activated this whiteboard. Okay, oops. Okay, so I think now I have the problem of this block. Okay. Okay, well. Okay, it's gone. Okay, now okay, before this one is some methods on training the parameters, and this is also still open research, basically. And now another problem is how to choose the ansatz. So there are plenty of choice. For example, you can also just pick some fixed ansatz and then wish for the best. And then you can also pick some hardware efficient ansatz. For instance, this is the ansatz that is native to your quantum computer. And then you can also choose adaptive ansatz. It's basically if you grow your ansatz, shrink ansatz on the fly. You constructed it gradually. So, for example, here are some well-known results in FQE. Here is an example of the bond dissociation curves. for several molecules, and this was performed on the IBM, and they were using hardware efficient ansatz. For instance, here for the hydrogen, they used 2 qubits, and you can see the results are very close to the actual ground states. And then for the lithium hydride, they need 4 qubits, and you can see that there are way more noise, and the energy tend to be overestimated. And then the more qubits used, the higher basically energy that you obtain. So it's further than the actual ground state. So the noise prevent us to obtain the ground state. So the energy is always higher if you have noise. So one way, as I mentioned before, to make your results much better is you perform error mitigation. So this is another classical post-processing. So for example, in this result, they perform error mitigation also on this hydrogen, and then as you can see that the mitigated results, they align with the actual ground state. And then for the case of lithium hydride, it is very close to the actual ground state. It is much better. So there are so many techniques for this error mitigations, and this is also still ongoing research. For example, the easiest one is you use the amplifications and then you do interpolations. So for example, you can actually just, when you have an ansatz with parameter theta, you can do it theta minus theta and then theta. So you have some redundancy of the gate. So more or less the noise is 3 times, and then you perform the actual ansatz, then you can just interpolate what is it with the no noise. Okay. This is zero noise interpolation. Okay, so this was the results of the finding ground states. And then now I would like to touch on the dynamic simulations of the dynamics. Okay. What does it mean by this dynamical simulation? So of course, you would like to, you start with some initial state size 0, and then you want to find out what is the dynamics, what is the final states governed by certain Hamiltonian age. And ideally, when you can express everything, your simulations go straight to your final state here. But then we can't, so we basically just chunk into a small time delta t. So this delta t gives you some detour basically, and then hopefully you will end up in the correct final state. And these terms, the evolutions of a small time t is often, it's called a propagator. One of the common method for these propagators is using trottarizations. So this is an example of the trottarizations after the fourth order. So this is the first order trottarization, second order, third, and fourth, basically. And you can notice that the lower the order, the higher the error, basically. And you can see that this trottarizations comprises of propagators of single Hamiltonian terms. So for example, a single term is looking like this one, and then you can implement this propagator as this chain of the gates. So this is quite standard. And then I just want to tell you later how this trottarization's complexity grows. It's not really clear, basically. So for example, if I have Hamiltonian of the hydrogen molecule of just 2 electrons, I have 15 Pauli terms, and then H2O has 1.5 K, for example. And then this is example of the propagators using trottarizations. So it's just on the hydrogen molecule. So here I actually count the gates using trottarizations. So I considered up to 4th order, and then I picked the best one. So for example, this is for some delta t 2.55. So for instance, I would like to obtain the I would like to approximate the propagator with the distance, for instance, 10 to the minus 4 error, and then how many gates I need is like 1.8K, basically using trottarization. So 1.8K of the quantum gates to simulate the dynamics of 2 electrons problem is overkill. So then what people try, also what I tried, is simulating the dynamic using the VQA. So it means that you're narrowing down the problem into compilations of this propagator for each Pauli term, basically, or just propagators of the entire Hamiltonian. Okay. So that's why I would like to touch on the compilation problem, because it's related to the dynamic simulations. So what does it mean by compilation? So compilation is having a goal of synthesizing a circuit C that approximates U. So I would like to compile unitary U, and then I would like to figure out what circuits that implement U. So you can just, you prepare a state, basically psi, and then you apply unitary U, and then you do some guessing here, and this should implement the inverse of the U, and then you have another step psi prime. So it means, so what we want is the, so the final state is the same as the initial state, if and only if the whole operation here producing identity for all state psi, basically. So instead of trying all this psi, or you can also randomly sampling hard distributed state, one of the way is using this Cherenkov state. So basically you prepare Bell states here, phi, and then you put your unitary, you implement unitary, and then this is where you perform the variation. So you perform your ansatz here, the C dega. And then you perform Bell measurements. So this Bell measurement is basically this one, this term here. So this is just the fidelity of your final state phi into the Bell state. So in this case, you can easily construct the cost function as 1 minus this fidelity. And then the cost function is 0, even only if this thing performing identity. So it means you approximate the U very well. So here, here is my results using this method, VQ method, basically, to synthesize a circuit to obtain this propagator of the hydrogen molecule Hamiltonian. So here I, in this, using trottarization, for example, here, you can see that this is growing kind of exponential. And then the other part here is just, this is, I'm using this VQE to this compilation that I shown you before. And then you can see that even for large delta T, the number of gates is maintained. Like, so this one, the full space is just the propagation for the entire space. And then the subspace is for a subspace, because this unitary, because here I have some knowledge that the unitary will maintain the number of electrons, so such that I only compile in the case of the electron number maintained. Details, if you are interested, you can check on this paper. But then you can see that the discrepancy is extremely large. So if you want to obtain the same error, for example, 10 to the minus 3 for delta t 4 seconds, for example, then if you want to use trottarization, you need around 1.6K quantum gates, compared to if you obtain this by the means of the VQA, that you can only need 18 gates. So it is so much better. And in this example, the gates are just rotations, polar rotations, and controlled rotations, basically. Okay, so the final part. Okay, I kind of have a lot of time apparently. So I will touch on the machine learning and in relation to these variational quantum algorithms. Okay, so the approaches on the quantum computing and machine learning, there are several approaches, and this is depending on the data you are working on and also the type of the algorithms that you run. So for example, if you have the classical data and then the classical algorithm, it means you are running the regular machine learning. And then if you have quantum data and then you run classical algorithms, it means you are trying to learn some quantum state, for example, using the classical algorithm. So for example, I think state tomography, I guess this is this type of algorithm. And then this one, if you have the classical data and then you have a quantum algorithm, then this is actually the most common type of approaches when people talk about the quantum machine learning. So you have your classical data and then you use quantum algorithm for learning. And then if you have the quantum data and then quantum algorithm, this is, I don't think it has ever been touched. It's open for explorations, basically. Okay, so you will see that in this case, if you have the classical data and then quantum algorithm, and then in this variational type family of machine learning, the difference between VQA and then quantum machine learning is, you will see that it's just the difference in the presence of the data training. Okay. So a quick reminder, maybe for the physicists. So here I would like to remind you about this kernel method. So kernel method is a very common method in the supervised learning. And then, for example, I would like to focus on this classification problems. So this classification problem is basically just distinguishing two sets of data. For instance, I have this data. I have a blue data and then the green data. And then these lines here basically describe my model. So I can have linear model. So this x1, x2 are called features. Then, for example, I can also have this kind of models, or I can have this circle models for this distinguishing. So the classification. And then the kernel method is basically the method you use this kernel. So a kernel K, this basically similarity measure between two data points. So if I have data points xj and x, and it gives you measure on how similar they are, and then your classifier, so your model, you can use this kernel to tell you which one of your data points. So for example, you already have you construct the classifier, this data, and then you can and if you want to compute which your new data X, where it belongs to, does it belong to the green or to the blue, you can just calculate the kernels, the sum of the kernels, and this is just the label. So basically it's kind of the average. And then this sigma here is some type of functions just to tell, okay, should you decide this is the green or the blue one, and then it will tell you which X it belongs to. Okay, and another one that I would like to remind you is the feature map. So the feature map is one of the technique that you are expanding your feature space. So for example, so you try to put your data set into a larger space. And then, for example, in the case of this support vector machine, if for instance, this is for instance, you have this 4 data. You want to distinguish the red and the blue, and then you map this into the 3-dimensional, and then in the 3D you can just put the linear model to distinguish these 2 data, and then this linear model is just requirement of this SVM. So for instance, in this small example, my future map F here is basically just mapping x1, x2 into x1, x2 extended to the x1 times x2, basically. So you can have this +1, -1 in the z, and then you can just draw a straight line here. So in this case, the classifier model is not defined in the actual space of the future space anymore, but it's defined on the future space, not defined the original space, I mean. Okay, and so I will iterate these ingredients of the machine learning and then translating it into the quantum computer. So the ingredients of machine learning and the basic, first you need the data. Basically, you have a set of input-output data. So you have input X, and then you have input Y, and then you want to find out what is the relation between this X and Y. And then the second ingredient is you need the model. So this is the some functions that input the your data, and also has a free parameters. So this is the parameters that you are going to learn, such that you can have this good model. And then hopefully your model can map your input to your output with a good precision. Now, how to tell how good is your model is you define this loss function, basically. So you obtain the loss from your model into your output, and then you try to minimize this loss such that you can have the good model. You have a good theta here. And then in the terms of involving the future map, it just means you are adding this intermediate step here. So you have the input data, and then you implement the future map. And then your model is implemented in this future space, and then you relate it to the output. Basically, that's it. And then this is a very interesting result from Schuld and Killoran. So if you so here they start with the inner product basically as the kernels. So what does it mean? So you have input space here, the X, and then you find a map phi here such that you have this future space F, such that in your future space you define this inner product. And then their theorem say that the inner product of your future space of your map state is actually also a kernel. So what does it mean? It means that you can have this future space on your model. And then it turns out that the future space F, it needs to be a Hilbert space. So you can see that this is very exciting correlation to the quantum because you can have your data and then your future space would be the Hilbert space, and then the inner product is basically here, for instance, it's just the fidelity. And then this is also a good future space because the Hilbert space is much larger than the input space, so it's like exponentially larger. So this gives you the freedom on this classification, as we saw earlier, like from 2D to 3D. Okay, so what does it mean with all of this? So it means that the data encoding, the classical data encoding is basically the quantum future map. So this is what people called classical data quantum embedding, basically. So you have your classical data, input data, and then you encode it into some quantum state. And then your model will be defined in the quantum state, in the Hilbert space. And then you find this in the output, correlation to the output. And here are some examples of these quantum feature maps. Basically, for example, you can just naively encode by its binary. It's for example, if you have some binary x101, your future map is basically this Pauli x I x, and this is just very naive, and then you're gonna need a lot of qubits. And then the second one, for example, the amplitude encoding. This is exponentially more compact because you encode it as the amplitude. So if you have a data set X, and then you encode it as the amplitude here, basically. And you can see that for arbitrary data, it will be very hard to prepare such a state. And then another ones that's quite common is rotation angle encoding. So here you have, okay, we always start from 0, and then you have, you rotate according to your data set here. So how does it implementations of quantum machine learning in this model? So here it's often called this variational circuits in the quantum machine learning. So here also we have before we have these 3 ingredients of machine learning. We have the data, and then because we are using the quantum future map, then it means we need some sort of state preparations. So we have this as X here. And then the second is the model. The model is here expressed as the unitary. So this is another parameterized quantum circuit, basically. And then you try to train this theta here. And then you perform some measurements. It could be some expected value of certain Hamiltonian or some any. And then you define, you do classical post-processing. So basically, this is the loss or the cost functions in the FQE. And then you update your theta, and then you train for all your data set, your training data, and then when you want to classify new data, you will find the output here. And if you compare with the FQE that we saw earlier, it is very similar, basically, except that this type of the classical data embedding side. And so, because it's very similar, the techniques that I told you earlier on the FQE can be implemented on this QML, basically, like all these gradients, the natural gradients, or the type of the ansatz, etc. Now, here is an example of some results by Furche. This is like the variational quantum classifier. So they have a set of data here, and then they like to classify if it's the red or the blue, basically. To be fair, they generate the data such that it is suitable for their quantum future map. So but they run it successfully on the real quantum computer. So they run it on this IBM, the quantum computer, and then they have this form of model. And then for their case, they use the parity. So for example, if the majority.
Cica, just friendly reminder that we have 10 minutes left, okay?
Yes. Okay, this is the last slide. For example, if the parity says odd, it means the red. If it's even, it means the blue. And then for their ansatz, they put just 4 layers, and then with the 4 layers, they have successfully classified the red and the blue 100%. It's very interesting. And if you're interested, you can check on their paper. So basically, that was my last slide. Thank you very much for your attention, and let me know if you have some questions.
Okay, Sicha, thank you so much for wonderful presentations. So I think it's very interesting talk. Chicha explained about the quantum algorithms such as VTA for chemistry problems. And then she also saw the important part of how to do encoding from fermionic to qubit system and how to create the parameterize the circuits by calculating some theta. And then they also saw the role of the classical optimizers and just introduction about the quantum machine learning. So we are now coming to the question and answer sessions. So if you wish to ask directly via audio or video, please raise your hand and we will invite you to speak. But currently, I try to read the question here in the chat. So please be informed that we have only 30 minutes left for Q&A sessions. So I will select some questions from the Zoom chat firstly. However, if your question has not been addressed yet due to the time constraint, because we only have 30 minutes left, please don't worry because we can continue the conversation with Chicha in the Discord channel later on. So I think we come to the first question from Sunil Karki. The question is, how do you do the fermionic operator mapping with qubit during the estimation of the ground state energy of the small molecule based on the VTA? So the question is technically how to do the fermionic operator mapping with the qubit during the estimations. Maybe Chicha can answer directly for the first questions.
Okay, so how to do the fermionic mapping? So it was the Jordan-Wigner mapping, just one of these example. Yeah, you basically basically just this mapping. You go to the second quantization, and then you have you maps the operator, and then you add this term such that the sign is correct, basically. I don't know if that answered the questions or I'm missing something.
So I think it also already solved and explained in the PowerPoint also, right? So there is three how to do encoding, right? Parity and also Jordan-Wigner. And then basically I think I guess that in practical you can convert directly to use Jordan-Wigner representation of the fermionic to qubit operators. And then the second questions. I saw someone raise hand, right? Who is? Okay. If not, maybe we come to the second question from Mukesh Kumar Kanore. So the question is, for many electron system, we have starting point as artifact as you described. In case of the system which don't have any starting point, so for example, no information about the initial basis state to describe the system. So can we use this technique to solve such quantum system? So the question is, yes. So the question is if we don't have any answers, I think, right?
So for many electron system, we have starting point as artifact. Yes. Yeah, you always start with the artifact because it's efficient. So you solve the non-interacting electron problems basically, and then you use the remaining okay, maybe, and then you use the remaining to solve the interaction parts using the VQE. So if you don't know which basis states you want to do, then you I don't think you can PQE can help. You need to have some knowledge. So for example, or you can just choose some orbitals. So here is very common. You use the s orbitals, you know, and this a single one electron orbitals. You just pick some orbitals, and this is actually also was it a QMA problem? It is hard. So I mean, in the future, even if we are able to solve, you perform PQE perfectly, and then the best ground state energy that you obtain must be expressible by your ansatz. So if my guess was using only s orbitals, then it wouldn't be as accurate as if I'm also involving the higher orbital, for example, like PD orbitals. So yeah, what you can do, you can just guess, and then there is no there is no way to verify if it's the correct one or not if you have a large molecule in the future. So I guess you can just add gradually more and more, and then if it converges, then you just stop there. I don't know if I hope that answers. No, you need to guess something first.
Okay, thanks, Sicha. I think the answer is mandatory, right? for predicting the wave function that close with the ground state. And then the third question is from the Gustavo Mangol. So the question is why, especially in slide 30, Cica, why does f have to be Hilbert space? Is it because the feature function have to be necessarily square integratable for the kernel to be defined? So just like confirmation, and also the important question is why does f have to be Hilbert space?
So yes, this has to be Hilbert space by the theorem. And there is some proof in it. Basically, you start with this product state, and then if you have this product state, and then you prove by gram metrics, basically, and then you have to prove that it is positive semi-definite. I can't really tell you details because it is like the proof of the theorem, and then yeah, apparently f has to be Hilbert space. Because the inner product actually is like one of the axiom of the Hilbert space. But yeah, I think check the paper. It is like they put the proper proof there. Okay, I think when someone is using this whiteboard, it destroys my my desktop.
Okay, maybe.
Okay. Okay.
If
So
you start search screen, maybe you need to avoid sometime.
okay. Okay, someone is raising hand.
Disable notifications. Okay, maybe I give a chance for the people who raise hands from Sunil Karki. Okay, maybe the operator can unmute the speakers of the Sunil Karki first.
So meanwhile,
Or-
I can answer the question
Okay.
5. Basically,
Yes.
please explain about parity
About-
and PQE with an example. So, for example, if you have 2 qubits, the probability of output is just 0, 0, 0, 0, 0, 1, 1, 0, and 1, 1. So the parity is just like the even is 0, 0, and 1, 1, and then 1, 0, 0, 1 are the odd. And you can this is just about the labelings, right? And you can say that the label odd is the green, and then the label 1 is the red. And then because the rest, you just decide this, and then the rest will be handled by your model. So you just parameterize this, you put your let's say you put your odd, your even data set, and then your parity outcome should be showing 0, 0, for example, or a 1, 1. And then you just training this way. I hope that answer. It's just like that.
Okay. Could I speak? Ms. Sunil Karagi.
Okay. I think Sunit Karki is already unmute. So
Yeah. Yes, first of all, I would like to say thank you to the speaker, okay? And I haven't get the actual answer. Okay, my question is that while you let's do the estimation of the ground state energy of like a small molecule like a hydrogen molecule, yeah. So all the operations we have to run in a quantum computer. And at the time, while you do the estimation of the Hamiltonian, we have to do Hamiltonian there. We have to make Hamiltonian. We have to it's formed from like electrons and electrons. We have to create from the electrons like that. Hamiltonian functions of electrons. So these electrons is a fermionic particle, yeah. And then while you do the mapping of this fermionic operator with the qubits, we have to do because we have to those things we have to do estimations on a qubit, estimations through the quantum computer based on qubits, yeah. So how do you do the mapping on that fermionic operator with qubits? So that qubits gives the results to estimate that to make the NGR circuit also, because we have to make the NGR circuits for the parameterization, yeah. So for parameterization also you are using machine learning there. So my question is how do you do mapping to do the operations of this fermionic operator with the qubits?
Do you mean that
without doing any mapping over there, we cannot estimate the minimum energy of the ground state energy from quantum computer. Mapping is the fundamental things over there. So you can a little expand about the mapping to things here, because first step is we have to do mapping over there for to estimate the ground state energy of the molecules or any steps, because we are not able to calculate the higher molecules, just only a hydrogen, helium, like 2 electron systems, like 1 electron systems, just simple things we are.
Mr. Sunil, I think your question is about the reason why we do the fermionic operator mapping with the qubit, right?
Yeah, qubits, because
Yes.
we have to we have to do the we have to do without mapping, so we cannot do anything else not there, because of everything we have to do based on qubits.
Yes, in quantum computer,
because we are using the quantum computer. If you are using quantum computer,
maybe if you would like to have more explanation, maybe we can discuss later, because we need to have a chance for the other to ask the question also. Okay, maybe you can also contact Cicia in the Discord channel later on and also discuss privately maybe, yeah. Okay, and then we need to go to the next question. And from the Elahe Afsane. So the question is, thank you for your great presentation. Would you please explain about the parity in PQC with examples?
This one I already answered.
Okay. And then because we have so many questions in here, so we need to select some questions. But if you feel that you are not satisfied yet, so you can have more conversation later on with Dr. Sicha in the Discord channel, okay? And then the fifth question is from Fortune Atsafax. What is the point of using gradient descent in the VQA algorithm?
The gradient descent, this one?
Yes.
Yes.
I think.
Okay. Because in the part of the learning, basically, you have you are guessing the theta, right? These parameters, and then for sure it's not optimal, or maybe, but then you go use this. It's quite a common method, gradient descent. You calculate the gradient, and then you pick to the directions of the going to the lower, basically. And then here you find a new parameter. So this was basically this one. And then you can update it again, and then you calculate again the cost function. So yes, we need the gradient descent because you want to find the lowest energy. Is that answer the question?
Yes, thank you, Cica. And then the next question is from Aswat Hanumara Tayapa. So nice presentations. Please comment on usage quantum machine learning algorithm for protein folding analysis by HHL algorithm. So I think this protein folding is more to life science. So maybe Dr. Richa, if you can answer, please. And but if you didn't know, because it's not related with the material science.
Yeah,
Okay, if you try to
yeah.
answer.
I have no idea, sorry.
Okay, thank you, Dr. Richa. And then the next question is in the page 5 of your slides. You determine the ground state energy by making the expectation value equation to be equal and greater than 0. So this gives scattering state. Why not considering when the energy is less than 0 in order to find the least energy?
This less than 0?
Yes, please see in the GDoc, Cica, and the last question in the page 5 of your slides. You determine the ground state energy by making the expectation value equation to be equal and greater than 0. This gives scattering state. Why not considering when the energy is less than 0 in order to find the least energy?
Oh, because less than 0. So this is just, okay, I didn't really see this less than 0 here. Let me check. Equation for equal to be equal and greater than 0. So the energy could be anything. It's usually negative values. And then I didn't really say that it needs to be larger than equal to 0. It's not written here. Maybe you confuse it with this gradient. So this is just the landscape of the energy, that it doesn't change anymore.
Okay, Cica, thank you for your answers. And then we still have time. And the next question is from Mriutu Jaya Sahu. Can we use optimization problem like CREB here? In general, how it's different from machine learning optimization as like gradient descent?
So I'm not familiar with this graph. If anyone can explain me what that is.
Okay, maybe this is he asked about different machine learning optimizations like gradient descent. So I think because CRIB Cica is not explained in here, might be later. So if you have opportunity to explore more, I think you can answer. We can discuss later on. And then the next question is, can you briefly explain how you use quantum machine learning to simulate dynamic again? So Bonnie Paul is requests you to explain again about how to use KML to simulate dynamic. Additionally, it's possible to study adiabatic quench dynamic in condensed matter system using quantum machine learning.
So I didn't explain KML to learn the dynamics. I think I just used the KML to do classification. So it's just the classifiers using quantum computer. And then the dynamics was just using FQE. So maybe I'm just guessing. Yeah, I don't know if you mean this one. So the dynamic simulation, it's basically just you operate the unitary, that is the solution of the Schrödinger equation, the time-dependent Schrödinger equation, which is E minus I HT. And then the simulations of the dynamics can be narrowed down into the problem on how to implement this unitary. And then the rest are just some techniques on how to implement this unitary, basically. And the possible study adiabatic quench dynamics in condensed matter system using QML. I am not really sure. No, I don't know.
Yes. Okay, Cica, thank you for your answers. And then the next question is from again, fortune at suffix, can we use only artifact after second quantizations?
So the second okay. So the second quantization is basically so you basically have the states as this occupation, and so it's only 0 and 1. But what does it mean? This is basically the presence of the Slater determinants. So the Slater determinants, it's obtained by the Hartree-Fock. So you need to have, because you actually don't know what is the basis. So this, so they come together basically. You have a guess of the orbitals, and then you have the efficient field. So you just put a single electron and then the average of the interaction of electrons. But this is a single electron problems, and then you don't know what's the solutions. You don't know what is this phi here. You also don't know what is the average of these interactions. So this is that's why you perform this Hartree-Fock. You do like 2 ways of optimization, and then you can have the orbitals the solutions of the 1 electron orbitals, and then here you form the Slater determinant basically because you want to have the antisymmetry property. So you have this product of the orbitals, and then this is basically Slater determinant. So single Slater determinant represented by this single number here. So it's like a presence or not presence, and then this is basically just representations of Slater determinants. So they can we use only Hartree-Fock? You can use Hartree-Fock to define your this occupation states, but then this one is not interacting electrons, so then that's why you use the phi-QE to obtain the rest of the energy by interacting these electrons. I hope this answers. Or
okay, thank you, Chicha. We still have around 15 minutes left. So if there is a question, please write in the chat Zoom. But I have a question, Chicha. You do some calculation on the ground state of the small molecule, right? By using rational quantum eigensolvers, and in this case, can you tell us about the effect of fusion ansatz? For example, we have already know that in general people using UCC as the ansatz for chemistry, right? So in which when we use UCC-SD and when we use another ansatz, for example, like that. And is there any a strategy to fix ansatz for example, not only small molecule, but also for a little bit larger molecule?
Yeah. Well, there is no standard way. So this UCCD ansatz, it's commonly used for chemistry problems because you hope that just by adding more of this, so the ansatz looking like exponential I, something looking like this, and then the hope that the more ansatz you put, the more accuracy you obtain. But this is also depending on the implementations. So for example, even if so this UCC ansatz is quite efficient for chemistry problems, but then implementing this operator, this looking like propagator, is also not easy. If you saw that, for example, you use this trotterization, you need like a lot of gates, and then it's depending on the quantum computer. So what do you have basically? But if you have general expressions, then you should, I think there is a possibility that you can just solve any type of Hamiltonian. It's not necessarily chemistry or just any Hamiltonian.
Okay,
So I don't know. I
thanks.
hope it answers.
Yes, okay, thank you, teacher. And there is question again from participant from Winston J. Mambongo. So the question is quantum machine learning applicable in the simulation of climate process, climate modeling? So maybe you can give some view or some
So
introduction if you understand, but if you didn't know,
yeah,
I think so.
I don't know how to climate modeling, but it's probably if you can do it in the machine learning, maybe you can do it in the quantum machine learning.
Yes, I think
I
so.
don't know. I have no idea.
So thanks, Cicia, for the answers. And then there is also questions from the participant. How can we verify if we have reached the ground stage, and with what level of certainty can we be confident in our results?
So this is a very hard problem, basically. So this ground state problem, as I mentioned earlier, it's like usually in the terms, it's either like NP hard or like what's it, the Merlin Arthur. So it means that there is no efficient verifier that tells you actually did the correct answer. So this is like open research problems. So for example, but what can we do? So for example, there is some ways to verify in general. So this is like another subject study of the verification. So what you do normally, no, so for example, one of the way to do verification, you perform the computations, and then you also secretly perform some tests. And then if your tests are doing well, so statistically they are statistically passing most of them, then you are sure that the quantum computer perform as it's supposed to be, such that the ground state that you obtain is the best. So there is no method to verify if you reach the ground state. So that's why this variational principle, it must reach the ground state for this entire Hilbert space of all possible states. But this is impossible. That's why you even narrow it down into the ground state of the given basis set, basically. So you fix the basis, and then even so, if you fix the basis and then you run it on quantum computer, it is not necessary that you obtain the ground state, right? That's why there is this verifications of the quantum algorithms, which in general give you certificate that okay, the algorithm that I was running earlier give me confidence, let's say 10 to the minus 4. Therefore, these assumptions give you another assumptions that my ground states give me 10 to the minus 4 of error. This is one of the way to verify, but to tell if this is the ground state, there is no way to tell. I hope that helps.
Okay, thanks, Cicia. I think how to verify for small molecule, I think it is still we can compare like the result from full configuration interaction, I think. But for
Yeah,
larger
if you can't solve this on the classical,
yes,
you can't classically, then how to verify on the quantum computer, right? So
yes.
so there's no way yet. It's an open research problem.
Okay, thank you, Cicia. And there is a question also in the Discord channels from maybe Cicia can also have a look in Discord channels. So here, Dr. Cicia, nice to meet you. I am studies a PhD student of material physics. How can we use machine learning for calculating properties of semiconductor material for various applications? So if you have a document, please could you share me by this chance. I would like to ask your collaboration on machine learning in predicting property of the material. Thank you again.
Yeah, so I don't really know, but in general, if you can formulate, so it was just about encoding the problem. That's basically the core of the quantum machine learning is this data encoding. So the data encoding, it also means the problem encoding. If you can first, if you can encode your problems of this finding some estimating some property of the materials classically, and then you do this encoding into the quantum state, then actually you can use this quantum machine learning. So it's basically if you find a way on how to encode your problem then into this framework, then you can find the solution.
Yeah, thanks, Icha. So we get hint that the problem is in encoding. Encoding is actually also a problem. And the next question,
big problem.
yes, okay. The next question is from Fortune in the Discord channels. So maybe Chicha can explain again what is throttlization, please.
Okay, throttlization. I'm trying to guess which. Okay, so so if you want to do dynamic simulations, this you just need to implement this unitary. So this unitary is basically the solutions of time-dependent Schrödinger equation, right? So it's just like exponent minus IHT, and then how to implement this on with a series of quantum gates. This is what we try to find out. That's why we use throttlization, because how to perform exponential of a matrix. And if the matrix is large, I mean, you can also use it numerically, do it, but then if the matrix is large, what can you do? So what you do is basically split them into the chunks. So the throttlization, so basically how to approximate this term. This is just, you have this Hamiltonian. Hamiltonian comprises the Pauli terms, right? And then this A and B, they are actually two sets of the Pauli terms which are non-commuting. So A is the terms that are commuting to each other, and then B is commuting to each other within themselves. But then A and B, they are anti-commute. So Pauli, it's either commute or anti-commute, basically. So you split these Hamiltonian terms into two subsets, and then these throttlization basically split the time t into n. So basically, if you see that there is like anti-commutating terms, so the terms is complicated, but then if you approximate it as the first order, so you can see that in these terms they are commuting basically. So that basically, if you do this exponential terms like manually, you have a lot of terms. If you have this, you have the quadratic, and then you have third. And then if you just use the first term, then you just multiply all this manual, like all the terms. So if you see that it has the n, so you also split the time into n. So hopefully that the error from neglecting the the commutation terms is small enough. If you have a small delta t, you can see it clearly by the expansion of the exponential terms. And then if you also include the second order of the expansion of exponent of a metric, then this is what you obtain basically, and then you just do truncation. You can easily follow the derivations of this actually, I think it's in Wikipedia. And then for each term, this one, so this is contains a set of commuting Paulis. So A contains like a lot of terms, like all these Paulis, Pauli 1, Pauli 2, Pauli 3, a string of Paulis that are commuting to each other. And then for each term, this A is a lot of terms basically, and then just a single term of the A itself is looking like this. So it has, this is just an example of a set in a subset of this either A or B, and then this is how you implement using quantum circuit. Yeah. So the point is the questions on how to implement this unitary, the solutions of time-dependent operator on the using quantum gates. So one of the ways using trotterization. I hope that answers.
Okay, thank you very much, Cica. So actually, there is also a question from Zoom chat, but because we only have 4 minutes left, so I think if your question has not been addressed yet due to the time constraints, so please don't worry, we can continue the conversation with Cica in the Discord channel later on, because we still have 4 minutes left. So I think the last question from me, Cica, can you give us suggestion to choose classical optimizers for the case of molecule from small molecule to middle molecule? I mean that usually people using gradient descent optimization, right? So I mean that if you have experience in using, for example, quantum natural gradient or others gradient-free algorithms, so can you give us insight on this effect to the accuracy of ground state energy calculation? So.
There is no well-known best way to perform this VQE, still open research problems. And then in my experience, using the natural gradient way, much better. You reach the ground state way much faster than using the gradient descent, because in the natural gradient, you also actually adding the informations you're adding informations of the structures of the quantum states. So if you notice that the parameters is in the real space, but then your state is in the Hilbert space, and then what you obtain is the probability distributions, which is on the different space. So this natural gradients give you some distance connection between the parameter space into this probability distributions different space. And that's why this was much faster. So in my experience, using the natural gradient is much better for this case. And then you can use this couple cluster ansatz, for example, because it's shown efficient for chemistry problems. It's more structured as well. And then on how to implement the propagator on the couple cluster ansatz, for example, you can use this compilation problem using VQE, as I shown earlier. And then there are a lot of methods to be explored. There are also low-hanging fruits kind of problems. For example, you can also doing warm-up. You do some, you have some libraries of the optimization you done before, and then you just increase the problems and do more optimization in the future. And because also this warm-up is helpful because it can help you to reduce the depth of the gates. So if you start with the good state that's close enough to the ground state, that maybe hopefully you can reach it. Although I think it's there is some research shown that when it's closer to the ground state, the complexity is harder. So who knows? I don't know.
Yes, okay, thank you, Cica. I think it's still open research, right? People comparing SBSA also for small molecule until very large molecule. So because the time is up, so please be reminded to all the participants. So if your question has not been addressed yet due to the time constraints, please don't worry. So we can continue the conversation with Cica in the Discord channels. And thank you for your amazing presentation, Cica. Thank you again for your valuable time and for your very good answers. And then thanks for all the participants for tuning in. And from now, for the operator, please stop the recording first. And we will now proceed with the contribute talk, which will be moderated by my colleague, Dr. Jumaida. Thank you very much and see you.
Yeah.
be delivered from Miss Flavia. Miss Flavia, are you already present?
Yes, hi. I'm sorry, I think I have a problem with my camera, so I can't put it on. I don't know what's going on. Sorry. But yes, I'm here.
Okay. Maybe we can try the share screen later. So
Okay.
yes. Okay, thank you. Before that, okay, good afternoon, everyone. Thank you for still joining with us on the third day of our workshop. My name is Jumaida Jatmika. I will be your moderator in this contributor talk session. Today's first contributor talk is from Ms. Flavia Alejandra Gomez from Universidad Nacional de La Plata, Argentina, with the title Supervised and Unsupervised Machine Learning Technique Applied to Skyrmion Systems. The speech time would be 10 minutes and 5 minutes for discussion. And on the discussion, you can write the question in the chat or raise your hand. And for Ms. Flavia, you can choose option disable annotation from others in the view option when you start to share your screen. And I encourage all participants to engage actively and ask a probing question. Okay, without further ado, Ms. Flavia, the time is yours.
Thank you. So I will share my screen now.
Yes, you can share your screen.
Okay, good. So can you see the presentation? Can you hear me correctly?
Okay, yes, I can see it.
Okay, thank you. So thanks to everyone and for the organizers to giving us the chance to present our work. This was done with collaboration with Diego Rosales. We are both researchers from La Plata, Argentina. And when we're going to talk about skyrmions here, we're going to talk about skyrmions in the context of magnetic systems. So here skyrmions will be formed by spins, classical spins, which we're going to illustrate as vectors, so as arrows. These skyrmions are formed in a lattice. So here and in all the talk, there will be a magnetic field, like here is this vertical arrow, and the colors, they will be assigned according to the orientation for the field. So red will be up, blue is down, and the other colors indicate other projections, right? They are just to help the eye. So on the right, on the left, you can see a structure of a single skyrmion formed in a lattice. And then on the right over here, you can see a skyrmion lattice in a lattice of spins, right? Again, the color blue is down and red is up. This skyrmion lattice in reciprocal space is seen as this triple Q structure. So this can be measured in neutron scattering experiments, and it is in fact the way skyrmions were first detected in MSI 15 years ago. The next year, they were measured in real space through microscopy, and the interest in skyrmions relies in that these textures have a topological property, which is that they can be mapped onto a complete sphere. And then you can assign something in the continuum that is called the topological charge, and since they wrap around the sphere one time, the topological charge is of absolute value 1. And this gives the skyrmions a lot of very interesting and particularly robust properties, right? They are more stable than, say, for example, ferromagnetic domains. And this is why they have been proposed for a number of technological applications, mainly in racetrack memory devices. So the thing is that if you take this, one of the first models proposed for skyrmions, so here in this paper where they measured in 2010 the skyrmions in real space, there is a comparison of a magnetic field and temperature phase diagram for the experimental and the theoretical part. And actually the theoretical part is the result of Monte Carlo simulations performed in this Hamiltonian on the left, where there is a magnetic field and there is a ferromagnetic exchange interaction and an in-plane antisymmetric Dzieloszynski-Morisia interaction between the spins, right? Everything is classical here. And if you look at low temperature, you can see you have basically 3 phases: the helices or spirals, a skyrmion lattice, and the ferromagnetic phase. And then there is a small region that is enhanced with temperature where you have these intermediate phases over here, where you have like the spirals are broken. We would call that bimerons. And then at higher fields, the skyrmion lattice gets broken and you have a skyrmion gas, right? The skyrmions are not in a periodic arrangement. And so here I show you again the Hamiltonian, and if you put this Hamiltonian and you do some classical Monte Carlo simulations, if you want to detect the skyrmions, you have to design an order parameter, which is the scalar chirality, which is the version of the topological charge for a lattice. And where the chirality is more intense is where you have the skyrmion lattice, and otherwise it will be 0. So again, I show you these three typical structures, the spiral, the skyrmion lattice, and the ferromagnetic. They are very easy to distinguish also in reciprocal space. But when you go to these intermediate phases, which are like these broken spirals, and when the skyrmions are not in a lattice, they have chirality, but it is not so easily related to, I mean, you can relate it to the number of textures, but you can't really distinguish them in real space or through the chirality. And that is actually where machine learning comes in. There have been a lot of works in machine learning and skyrmions. I'm only mentioning these ones of 2018, where since these three phases are very clearly distinguished, you only need a feed-forward of one layer neural network, and so these sectors at low temperature can very easily be distinguished. But then when they apply this classification to snapshots at higher temperatures, see here in this red panel, this green panel, the circles show you where the skyrmions should be, but then the network assigns skyrmion even at higher temperature, right? But it works very well for low temperatures. Our proposal here is to use a convolutional neural network where we're going to classify between these three phases and also the intermediate ones, the bimerons and the skyrmion gas. And since we want to build a complete phase diagram to classify the whole range of temperature, we also introduce paramagnetic high temperature phases, right? So this is a convolutional neural network. We use Keras and TensorFlow. And this has, I think, 4 layers because it's a bit more complicated to work with the intermediate phases. And what we're going to do is we're going to train and validate in very low temperatures snapshots from Monte Carlo simulations. We only take the component along the magnetic field. So we guarantee that the CNN does not learn the chirality, right? It only works with the snapshots as images. And we take some snapshots at high temperature, right? Very low temperature and a few in the paramagnetic phase to classify between these 6 phases. And then we're going to apply this classification to a wide range of magnetic field and temperature. And we only train and validate the network for some scale of the skyrmions and spirals. And then we're going to test it in a scale of skyrmions that it has never seen, right? Like bigger skyrmions, for example. So our data set is of about 2,000 snapshots, and we are confident that we have an accuracy of about 90% in the test set. So here I show you in the first column is the results of what you would do if you do simulations and you calculate the chirality. These are the phase diagrams. Remember that the chirality is not something that the CNN can learn. And the rectangles show where we take snapshots for training. So in all the rest of these phase diagrams, there will be snapshots that have never been seen by the network. Then in the second column, we apply the classification to the snapshots, and you can see that you have these 6 phases, and there is a very good agreement with what you would do if you look at the chirality, right? So in the first row on the top over here, some of the snapshots have been seen by the CNN, but in the bottom row, it is another scale. They are bigger skyrmions. And still, there is a very good agreement. And to emphasize the need to use CNN, that it takes the snapshots at images, and convolutional neural networks are optimal for images, I compare the same analysis with other simpler techniques, like support vector machine and random forest. And you can see that these phase diagrams have nothing to do with the ones I showed you before. If you can compare, you will see that especially for higher temperatures and for the other size of skyrmions here on the left, you can see that they fail. They are very good to classify the phases that they have seen at low temperature, but not the higher ones. And then let me briefly comment on what we're doing on unsupervised machine learning. We're going to use convolutional autoencoders. So an autoencoder or an AE is basically something where you put an input image, it decodes it, encodes it, and then it decodes it into an output image. If the decoding works, the difference, so the error between the output and the input will be small. And that is the idea. We use anomaly detection, which is a technique that tells you that if the error is large, then there might be something different there. Different to what? Different to the training set you have used. And here as a training set, what we do is we put the input is a set of about 5,000 or 6,000 Skyrmion lattices that we built analytically, so they are perfect Skyrmion lattices of different Skyrmion size, different magnetization, and different orientation. Here, this is only a cartoon of the convolutional autoencoder. It actually only has one layer. And as to optimize it, we calculate the mean square error, the difference between the outputs and the inputs. And now what we're going to do is, so you can see that, for example, here, if the input is a disordered lattice, the output is actually something that is not very good, right? Because this was trained for Skyrmions. But when we use it for Skyrmions, we actually don't see a lot of differences. And now what we're going to do is we're going to apply it to Monte Carlo simulations from 3 lattices, which are the same models I showed you before, but for triangular lattices. So a triangular, a Kagome, and a Kagome lattice where there is an additional out-of-plane interaction. So now I'm finishing. You can see here at low temperature, the yellow curve is the chirality. So you can see, and the red is the error, right? It's only putting the snapshots at low temperature through the convolutional autoencoder and calculating the difference between the output and the input. And you can see that, in fact, the error is up for the spirals. It goes down to the minimum in the Skyrmion lattice, and then it goes a bit up in the ferromagnetic. So the error can actually distinguish between the 3 main low temperature phases. And then you can find the same for the Kagome lattice. But if you go to the 3rd model, which is the Kagome lattice with an extra interaction, you see that something happens here. It goes up a bit, the error. And since we are snapshots, we can go there and look what happens. And we can see these phases. The difference between input and output is not bad. But this phase is not something that we might find at high field, right? It's actually a glassy bimeron phase. We have studied this model in another context, and it is something exotic. And the only thing we had to do to find this is to actually study only the error between input and output, right? It is not something that you will see, for example, inspecting the chirality here in this phase diagram, right? You don't see anything in the chirality, but you see something different when you inspect the error. So basically what I've shown you is our approach with supervised and unsupervised machine learning, working with Monte Carlo simulations for Skyrmion systems. And I hope that I've shown you that these are important techniques to support this kind of research. So thank you.
Okay, thank you for the presentation from Ms. Flavia. And now let's jump to the Q&A session. The first question is from Mr. Sunil. Can we use the Skyrmion lattice-based material to store the quantum information?
Okay, so this is a very good question. Actually, there are no actual implementations, but there is a lot of work. And you can see here, for example, a reference in how they propose that Skyrmion can be used to actually build a qubit, right? But still, this is a lot, of course, speculative work. But yes, there are some people that are researching the use of Skyrmions as qubits, for example.
Okay, I hope it answered the Mr. Sunil question. Okay, let's jump to the next question. Is Skyrmion is quantum system or classical? If it is quantum, how to use Metropolis? Thank you.
Okay, yes, thank you for the question. So I said it very briefly in the beginning here, since we can draw them, these are arrows, right? So these are classical spins. So, but then, even if so for Skyrmion system, it is enough to think of the Skyrmions as arrows, as classical Heisenberg spins, magnetic moments. But in the recent years, very recent years, like in the last couple of years, there have been studies on studying the possibility of having quantum Skyrmions. In that case, of course, you will not be able to work with Metropolis. You will have to work with something like exact diagonalization for a small system, or maybe DMRG or something like that.
Okay, thank you for the answer. Okay, let's jump to the next question from Mr. Mohammed Eloni. Can you explain in simple way what is exactly a skyrmion?
Okay, thank you. So basically, so here, for example, you have a lattice of spins, right? And if all the spins are up, this lattice will be, everything will be red. So it will be a ferromagnetic arrangement. And a skyrmion is a particular arrangement of the spins. So this will be over here. The colors are just an indicator of how the spins are oriented. They are just to help the eye. So red will be up, and blue is when the arrow is pointing down, and yellow, for example, will be when they are in plane. And that texture, which is composed with several spins, right? A lot of spins configure a skyrmion, and that is what you call a skyrmion. The thing is that they have a topological property, because if you put all the spins, all the projections of the spins connected by the tail of the arrow, you can see that you cover a complete sphere. And that is a topological property that is called the topological charge. But basically, a skyrmion in this context is simply the way the arrows or the spins are ordered, right? So there are several other things that are similar to skyrmions, but it's simply a texture. So if you have an L ordering, you have one arrow pointing up and another pointing down, right? So this will be an L. A ferromagnetic is all the arrows pointing in the same direction. A skyrmions is that all these spins are arranged in this sort of particular pattern. I hope that answers the question.
Okay, thank you. Okay, let's jump to the next question. How do you obtain or create this skyrmion data for training and validation? From Mr. Eddie.
Thank you. I went very fast here, so I understand the question. What we did actually is we took this Hamiltonian, right? And we did this Monte Carlo Metropolis simulations. And I mean, anyone can do this. This is a very simple Hamiltonian. And what we did to train and validate is we took the low temperature snapshots. So for example, they would be things like this, right? Things that are very clean. And we only took the component that is parallel to the magnetic field. So of the three components of the spin, we only take the Z component. And actually that's that. We only took snapshots, only pictures of the arrangements, only that information. And that is, so we did a lot of simulations to get about 2,000 snapshots. They're all independent copies, of course.
Thank you. So we have 1 minute left, I think. So next question is, how about choosing or mixing TEM images as input along with MC input? And what is the criteria for MC input to qualify as a correct or adequate input? Thank you.
Okay, so if I understand the question, it would be what is the criteria to how do I select the input, right? Is that the question?
Yes.
Okay. Yes.
Okay.
Okay. So if
yes, you can answer first.
Okay. If I understand correctly, so yes, that is the part that is under the table, right? The part of classifying the snapshots before putting them in the machine learning algorithm is like the part that takes a lot of work, right? The processing of the data. So basically there, what we did is, you know, that at low field, you will have spirals, and when you will have ferromagnetic at high fields and the skyrmion lattice. But then, especially in the intermediate ones, what we had to do for this, to build this data set, is we had to inspect snapshot by snapshot to see what was going on. So actually, a lot of that part of the work, especially for the intermediate phases, is done by hand or by eye, right? We have to go, look at the simulations, and then we label them by hand to build the training and validation data set.
Oh, okay. Thank you for the nice answer. Unfortunately, the time is up, and there are several questions. Maybe for the unanswered question, you can ask directly on the Discord channel, and you can get in touch with Ms. Flavia. Discord channel on the #contribute8. Okay, thank you.
Okay,
Thank you, Ms.
thank you very
Flavia.
much.
Thank you.
Thank you.
Thank you. Okay, I will give a time for operator to stop the Zoom. It's okay. Maybe it's okay. Okay, let's next jump to the next contributor talk from Mr. Dominic. Mr. Dominic, are you ready for the presentation?
Yes.
Oh, okay. Okay, thank you.
Cool. Can you see me and hear me well?
Yes. I can see you and hear you well.
Okay, perfect. Let me just try sharing the screen.
Okay. The next contributor talk from Mr. Dominic Escoffier from Harvard University with the title Approximately Symmetric Neural Network for Quantum Spin Liquids. The speech time will be 10 minutes and 5 minutes for discussion. And you can write the question in the chat or raise your hand during the discussion. And I encourage all participants to engage actively and ask probing questions. Okay? Without... Oh, yes. Oh, okay. I'm sorry, Mr. Dominic, you show the presenter view?
Okay,
Can you disable the presenter view?
Let me just try swapping it. Is it better now?
Oh, okay. It's better now.
Okay, perfect.
Okay. The time is yours.
Awesome. Wonderful. Yeah, thank you so much for the invitation and for the organization of this very interesting conference. And today, like, what I wanted to talk about is just this recent work we just put on archive last month, which is on these approximately symmetric neural networks for quantum spin liquids. So without further ado, let's get down to it. So I guess, like, a leading motive of this conference is that we have seen like some tremendous recent AI advances, like in multiple different fields. But then, one of the questions, which is, I guess, also like very fundamental, like, and which we see a lot in here, is like, how and can these AI advances be like successfully applied to some challenging condensed matter problems? And as many other speakers, I would like to perhaps have an answer to it being qualified yes. And just to present, our work on this, on like one of the challenging condensed matter problems, which are quantum spin liquids. So what we created is like this kind of like a tailor-made neural network architecture for trying to search for ground states of some quantum spin liquid models. And in particular, we were able to reach state-of-the-art energies up to systems of size of almost 500 qubits. We're able to apply our approach in contrast to, for instance, quantum Monte Carlo to like some sign problem full Hamiltonians. And furthermore, we can show that like our neural network architectures have this degree of interpretability to them, which is related to this notion of quasi-adiabatic continuation. So that's kind of the today's talk, and we'll just get into more details now. So maybe just looking into outline, we'll talk about quantum spin liquids, we'll get into symmetries of them, we'll talk about so-called a construction of neural quantum states, and then like we'll talk about our architecture and basically like what are the benefits of it and what is the streak of interpretability. So let's see. So let's start from like quantum spin liquids. So what are quantum spin liquids? Well, quantum spin liquids are these like exotic phases of interacting quantum spins. They have like some pretty interesting properties. They have like no magnetic ordering. They have some fractionalized excitations. They have long-range entanglement, topological order, plenty of rather exotic properties. And what is cool about them as well is that we can really realize them in a lab, which was realized one of the first times like here at Harvard and like by a team at Google. And in a sense, like, we're just able to show that these sort of phases can really be simulated on like already quantum hardware we have now. So this is also of some experimental relevance. So then, what the question is like, okay, what is the paradigmatic sort of like spin liquid Hamiltonian? And this is so-called a toric code. So on toric code, like what we do is, for instance, we might consider a set of qubits defined on like the edges of a square lattice with, say, open boundary conditions, and then define a Hamiltonian, which contains like these two mutually commuting terms, like just products of like poly X operators on vertices, around here. And then, poly Z operators around each plaquette, or like each little square in here. And then like one of the interesting properties of the ground state, as Kitaev has shown over 20 years ago, is that the ground state of this model fulfills like a simultaneous +1 eigenstate of all possible AV and BP operators. And what it means is that, that basically, like if we apply another AV operator to a ground state, which already contain like one AV operator, like basically you can just, it creates, a configuration which also be a part of the ground state as in here, and here and here. Like the upshot is that what is interesting about these quantum spin liquid phases at the toric code fixed point, there's this exponentially large group of local ground state symmetries. We can act, at an arbitrary point with like these AV operators, for instance, and then like we'll still remain invariant. Like our ground state will still remain invariant under this. So this is toric code fixed point. But then we talk about when we talk about true quantum spin liquids, also within the experimental platforms, like we never see just exact fixed points, but what we're seeing is like just sort of an entire phase. So basically, like we had these two first terms on the left, but then like we're also adding, for instance, like a bunch of different magnetic fields or some other perturbations to it and real experimental setups. So then it turns out that this quantum spin liquid phase extends to like some finite portion of the diagram, and basically, we just have like this entire topological phase for a finite value of hx and hz. We ignore hy for now. And then the point is that these AV symmetries of the ground states, which were exponentially many in the past, are not exactly preserved. But then there are two ways we can think about it. Either to think that, for small values of like hy and hz, like these AVs are still approximate symmetries of the ground state. Or it turns out that like for this construction of like quasi-adiabatic continuation of Hastings and Wen, we can still construct like some modified like finite depth unitary dressed operators, AV prime, which will still be exact symmetries of the ground state. So these are two perspectives, and we'll show how neural network fits into it and discovers both actually. So the problem about the latter perspective, though, is that like these symmetries, like we do not know how to write them down exactly. And this is why, like as a construction principle, like these neural networks will construct will be only approximately symmetric, because like these operators AV we know how to write down, and basically you can try imposing on a neural network. So this is kind of like the key idea in here. And in order to realize this goal of like trying to simulate this quantum spin liquid model with neural networks, we'll also utilize the neural quantum state construction, which basically, there are very three simple key ideas in here. You start from a particular state psi, you decompose it in a particular basis. Say like this S is like a computational basis or something, and then like you treat S as a bit string to be an input to a neural network. You multiply it by a bunch of weights, and then like you get a coefficient, a complex number out of your neural network. It's going to be this coefficient of the expansion of like an arbitrary state, of an arbitrary quantum state. And then like, after you sort of represent, it's this quantum state as a neural network in this way, you just perform energy minimization, which you can do by like Monte Carlo Markov chain like something. And then like after you've evaluated energy, you can calculate like gradients and stuff like that, and basically like update, your energy with respect to the parameters of the neural network. Just try to minimize it, using some gradient descent or some more advanced optimization algorithms. So this is the key idea. So then like what we're going to do, is just to try to understand like, okay, so if we just try to have like a naive neural network architecture, just like, a feed forward, like single layer neural network architecture in here, like what would be an issue with applying it to this to the case of quantum spin liquids? Well, like what we want to see on the left is just like this nice energy convergence curve to a ground state. But like what we're often seeing is like what happens on the right. So basically like we just get stuck in local minima. And this is like one of the main issues with like trying to apply, this neural quantum states to quantum spin liquids. But what we've seen just before is that, that this quantum spin liquids, even like the entire phase contains this like exponentially large group of approximate symmetries, which if neural network knew about, maybe we can improve the, its performance for this. So this is the key idea in here, and this is what we're going to do. But then like getting down to the bones of it. So let's see. So how do we construct like a fully symmetric neural network architecture? Well, like we can just try to make, sort of like two inputs to the neural network, like, related by a certain group element to produce the same output. And this is, sort of like very standard in machine learning. And this is like what we might require for like so-called equivalent neural network constructions. And then like if we want approximately symmetric networks, then like, we can just try to impose this condition approximately with a certain epsilon here. So then like, how do we do it in practice? Well, we construct the neural network architecture in this way. So, we just input like a bunch of bit strings in here. There'll be like these exact symmetries like, present as we mentioned before, but we only, sort of like know these symmetries in here. So like, we try to impose them, but like we cannot impose them like exactly exactly, right? Because what we need is sort of first try to, to basically like break these symmetries slightly in order to incorporate for sort of these approximate symmetries. And this is like what this non-symmetric block is doing in here. So it's basically mapping from approximate symmetries to exact symmetries. And this is like what the first layer of a neural network is doing, or like for a first block, which is non-symmetric. And then like, from there, like you should have exactly symmetric problem. And then you're just trying to impose the symmetries exactly on this block of a neural network. And then just, it's sort of like trying to impose these symmetries and then just output the complex amplitude in here. So this is the main idea for the neural network architecture. So now like, is this thing working? Yes, like if you go to like some small system sizes, what you're seeing is the baseline neural network architectures are being stuck and, local minima. So, all these different curves in here, like red curves, correspond to just baseline, different hyperparameters, different initializations and stuff like that. And the architecture we've created, this approximately symmetric one, basically like converges to the ground state very well. And this is like orders of magnitude, like 4 or 5 orders of magnitude of a difference in terms of like these small system sizes. So in other words, like, I've motivated this as like, we want to escape local minima. And indeed, like, and here you can see that this, sort of tailor-made neural network architecture is doing that. So this is like one hopeful result, but this is like 24 spins. So what's the point? We can do exact diagonalization here. So then we scale up, and like what we can do is like, just, compared to like DMRG methods and like so tensor networks and quantum Monte Carlo, and then see that like at every point, like we see very nice convergence to these results on larger system sizes up to like 16 by 16, which is like when you calculate the number of spins, it's about like 480. So these are like pretty big system sizes, not accessible to DMRG, for instance, already. And what you're seeing is like for large system sizes, for down here, like, I don't know, a few hundred spins, you see that like this neural quantum states we've designed for this purpose, like basically are beating all the existing methods by a slight edge. But still we're, just able to show that we are state of the art in this. So therefore, the question is, okay, so I've spoken, about all of this, but then there's the DMRG, there's quantum Monte Carlo, so, some other numerical methods. So the real question is like, where do we win, right? And then like what I would like to suggest is like when you have sign problem full Hamiltonians on finite 2D clusters for large system sizes, this is like where this method seems to be like, state of the art as we know. So in other words, like, this is like, basically, like there exists no other numerical methods we are aware of, like which would be able to deal with this. And then like the way we demonstrate this is, for instance, like to create a phase diagram for like a finite value of an HY field, which introduces a sign problem, precludes using methods like quantum Monte Carlo and stuff like that. And then we can draw this like nice phase diagram, for a finite value of HY field, which no other method on finite system sizes can do, as we are aware of. So in this sense, this is like a unique tool as of now for that.
I'm sorry.
Mm-hmm.
Yes, the time is a little bit tight, so can you make a little bit faster? Sure.
Yeah. I mean, there are like, no worries. There are like maybe 2-3 slides left, so we're almost there. Great. So now like, this is where we win. So now the final piece is like I've promised interpretability. So it turns out that like, I've claimed that this non-symmetric block maps from approximate symmetries to exact symmetries. So then like, the way we can test it is just like, by trying to fix the sort of like non-symmetric block identity, train the symmetric block at this, along this sort of fully symmetric line at hz equals 0. And then like, do a step 2 where we fix the we fix symmetric weights and we train non-symmetric weights. And then like this thing, if this training is successful, then it demonstrates in this setup the hypothesis we're able to show that basically you map from approximate symmetries to exact symmetries in this non-symmetric space. And this is indeed what we are seeing. So it shows, in this setup that basically we have like an interpretable neural network architecture as well. And this is like related to this quasi-adiabatic continuation that we're able to like, in a sense, learn these emergent Wilson loop symmetries. But then like getting to the bottom line, the conclusions, like what we've shown is like, this approximately symmetric neural network architecture, which is, able to escape local minima, which is scalable, which, it can apply to sign problem full Hamiltonians, and which is interpretable. And then the next steps, like, for us is just trying to investigate, some dynamics problems and like, some more complicated quantum spin liquid problems, chiral spin liquids, direct spin liquids. I mean, I think that this is, sort of opening up like a little bit of like an avenue of just trying to tailor your neural network architectures for some quantum spin liquid or like in general quantum many-body physics problems in this way. So with that, I would like to conclude and thank my collaborators. Welcome any questions you have. Like you can check out our paper you have in here, or like just a quick introduction to like neural quantum states in general below. And with that, I would like to conclude. Thank you so much.
Okay, thank you. Thank you for the fruitful presentation. Okay, let's jump to the next session is Q&A. Here we have several questions. The first one is from Mr. Muhammad Eloni. What is topological order and how it is different from topological insulator? Okay.
Yeah, so this is a good question. So like, I guess, what we're talking in here is just like, topological order, like, I guess, people often use this definition where basically when you consider ground states of some quantum systems, but basically these ground states have a ground state degeneracy coming from, which is dependent on topology of your space. So for instance, when you put your sort of like quantum system on a torus, you have some non-trivial topology. And then the ground state degeneracy should be dependent on this topology. And furthermore, this ground state degeneracy should be robust to arbitrary local perturbations. So this is like what we mean by, it's sort of like topological order and quantum systems. It's like a bit different to like, sort of, I guess more, it's a little bit different to like topological insulators, but maybe we can talk about these like in more details, like, afterwards.
Thank you for the answer. Next question is from Mr. Shahir. What is meant by the toric code phase? Please elaborate it. Thank you.
Sure. Yeah. So maybe just going back to that slide. So, okay. So in here, right, like we're talking about just the Hamiltonian with like these two first terms in here. And then like there's no free parameter in here, right? Like there's just like, basically, AV and BP term, and that's it. But then like, in here we can introduce like few extra free parameters. So HX and HZ, like ignore HY for now. And then basically what we mean by a phase is that, as you tune the values of HX and HZ, the same sort of topological order properties of this system remain. So in other words, there exists like an equivalence class of like some states under a certain property, which extends to finite values HX and HZ. So this is what I mean by a toric code phase in here.
Okay, thank you. Next question is, why is so much noise in your result?
Okay. So is it like referring to, I guess like maybe this slide in here? I mean, okay. So I guess the noise in here, like, at first, like when you look the curves, for our architecture, the noise is actually pretty small in terms of like the time variation. And then like, the noise is present very much for like these baseline neural network architectures. That the noise is coming from the fact that first, like you optimize the parameters, it's sort of in an online way. And second is that, you're sampling in order to evaluate the energy. So some of this like coming from like sampling uncertainty, but some of it, as you see for like different architectures, is just coming from the fact that you have not chosen the architecture right. So in other words, like, for our results, actually the noise is pretty small compared to like any existing sort of, neural network architecture would run on this system.
Help answer your question, Mr. Shahir. Okay, next question is, if I understood correctly, you are using equivariant layers for the symmetries. Thus, the implementation for these approximate symmetries involve changing the weights in this layer, or is the non-symmetric block unrelated to the equivariance part?
Yeah, this is a great question. I mean, I guess like, I have this slide in here of like an actual architecture. So like, again, I've mentioned that there's like a non-symmetric block and a symmetric block. And the point is that like the symmetries, you're just imposing like within the symmetry block. And then like, the non-symmetric part is like fully independent. It has like unconstrained weights. And these two parts, like they work like pretty independently, as it's sort of like described in the in this like approximate to exact symmetries part. One maps from approximate symmetries to exact, and the other one just imposes exact symmetries. They're like fully independent. Yeah, that's a great question.
Okay, thank you. Maybe this is the last one, the last question. How do you deal with the magnetic order at absolute zero temperature based on NQS? Thank you.
Yeah, so I guess like if I understand correctly, it might refer to basically when we have this Hamiltonian in here, it might basically like refer to the case where we have, for instance, like very large values of like HZ or like HX field. Then indeed, like what is going to happen, like when you look at this phase diagram in here, it's just like when you go like very far away in here, like you'll have like just a Z paramagnet or like a this direction X paramagnet. So like, neural quantum states like are very flexible ansatz, and they can, just very easily capture this. Like one idea is just like, trying to think about them as like powerful function approximators, and you can approximate any function you want with, pretty much like an arbitrary precision as you scale up the number of parameters in here. So magnetic phases are like pretty simple. And what is hard for neural quantum states is to learn sign structure, is to learn, superposition states. And in here, we're trying to win with like, representing superposition states by having this fully symmetric neural network architectures, which tells you like what are different components of the superposition and how they should be weighted. So this is where we're sort of like winning in this approach as well.
Okay. Okay, thank you. Maybe the time is up. Thank you for your nice presentation, Mr. Dominic. And actually, there are some questions, but you can write in the Discord channel on the Day-2 hashtag contribute 9 for get in touch with Dominic, and we hope we can make us a collaboration. Okay, thank you, Dominic, for your time. Okay, maybe
thank you so much.
Okay, thank you. Okay, maybe I give a time for organizer to stop the recording. Okay, maybe okay. This is it, the first half of this session. So we can start again on the 1 p.m. on CEST time. So please be careful on 1 p.m. CEST time. And I remind you that maybe it's preferred to stay on the Zoom during the break, because maybe there are some trouble or something. So it's better to you stay on the break room during the break. Thank you. That's all for me. Have a good lunch. Thank you. Thank you.
Tahta indah terukir prasasti, tata krama terlukis abadi. Di tanah ini kita terlahir, langit memanggilnya tanah Nusantara. Langit memanggilnya tanah Nusantara.
Once upon a time, there was a princess who lived in a beautiful land, which everything in it lived peacefully. She spent all her time in the depth of a forest with her 8 little friends. There was a hidden secret place, so magical and dangerous at the same time. This is the story where the culture had start. And now, let me take you on a journey. So welcome to Wonderland, Indonesia, the sacred Nusantara.
Sumping dari Jawa, datang nih cibu bawa kepiting 2 ekor. Jajabu dalam belang api, cak hidung gigi ronggang. Sapi ketawa dulu di pancung raja tunggal. Sinanggar tula tula, sinanggar tula tula tula, sinanggar tula tula tula, sinanggar tula tula tula, sinanggar tula.
One day, at another time, a girl will unearth the civilization that has been buried deep for so long. See you on that day.
Tahta indah terukir prasasti, tata krama terlukis abadi. Di tanah ini kita terlahir, langit memanggilnya tanah Nusantara. Langit memanggilnya tanah Nusantara.
Once upon a time, there was a princess who lived in a beautiful land, which everything in it lived peacefully. She spent all her time in the depth of a forest with her 8 little friends. There was a hidden secret place, so magical and dangerous at the same time. This is the story where the culture had start. And now, let me take you on a journey. So welcome to Wonderland, Indonesia, the sacred Nusantara.
Sumping dari Jawa, datang nih cibu bawa kepiting 2 ekor, jajah budel melangapi cai dong gigi ronggang, sapi ketawa dolong dipancung raja tunggal. Sinanggar tula, sinanggar tula, sinanggar tula, sinanggar tula, sinanggar tula.
at another time, a girl will unearth the civilization that has been buried deep for so long. See you on that day.
Tahta indah terukir prasasti, tata krama terlukis abadi. Di tanah ini kita terlahir, langit memanggilnya tanah Nusantara. Langit memanggilnya tanah Nusantara.
Once upon a time, there was a princess who lived in a beautiful land, which everything in it lived peacefully. She spent all her time in the depth of a forest with her 8 little friends. There was a hidden secret place, so magical and dangerous at the same time. This is the story where the culture had start. And now, let me take you on a journey. So welcome to Wonderland, Indonesia, the sacred Nusantara.
Sumping dari Jawa, datang naik cibu bawa kepiting 2 ekor, jajah budel melangapi cai dong gigi ronggang, sampai ketawa dolong dipacu raja tunggang. Sinanggar tulah, 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 sinanggar tulah, 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 sinanggar tulah, 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 sinanggar tulah.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science. Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science. Humans have always been curious. Why is the world the way it is? How does the world work?
Okay. Okay, welcome back, everyone. Let us start this session of the last contributor talk. So I am Muhammad Sofi Uktari, and I'm a researcher from the Research Center of Quantum Physics at BRIN, Indonesia. And I will be chairing this last sessions of the contributor talk. The speaker is Miss Fatima Jahra Siori. Miss Fatima, are you here already? Can you please answer me? Miss Fatima, are you here? Can you hear my voice? Oh, okay. Maybe let us wait just maybe a few minutes for Miss Fatima. Hello, Dr. Abir, do you represent Fatima? Let us wait one more minute. All right. Okay, so unfortunately, the speaker is not here. So let us just move on to our next session, which is the hands-on workshop for the second day. So it will be delivered by Mr. Yusrul Hana. Are you here, Mr. Yusrul? Can you answer me?
Yes, I can hear you, Dr. Sophie.
Okay. Okay, nice. Are you ready? How are you?
Yes, I'm ready. It's anytime. Okay.
Okay. Please share your screen.
Okay. So, okay, maybe I'll give start screen first. Yes. Anyone can see my screen?
Yes, just maybe make it full screen.
Okay. So, yeah. Good afternoon, folks. Welcome back to the second hand session in today. So today
I'm sorry.
is the yes.
Could you make it full screen?
Okay. Later on, I will give some information to participants because I will move the switch between.
Oh, all right.
Oh,
all right. Understand.
Okay. Sorry, Dr. Sophie.
Sorry.
Okay. So, okay, we'll back again. So today is the last day hand-on session in these events. So please, I remind you, if you have any question about previous hand-on session about quantum computing, please ask through the Discord channel. And also please through my GitHub, I have updated some code into my GitHub until today, like machine learning. So if you attention with the information from the workshop admin, so please. Okay. Okay. Today I would like to give you some deliver information about how to machine learning to dealing with the condensed matter physics. So before we going to jump into the code simulation, but the first thing is I would like to give you some brief information about what to like to simulation is. Okay, so today I would give you some two example. For example, such as classical icing model and also Su-Server-Hager SSS model to predict a fast transition of this model. Okay, jump into maybe the brief history of the classical icing model. So as far as know that classical icing model is represented by this Hamiltonian like this. So this one configuration is a spin up and spin down only. And then when we have a spin up, and we get some energy minus g, and we have got some the spin up and spin down, the energy plus g. But it should be noted that a probability of configuration of the spin affected by the temperature. So when we increasing temperature make a different from maybe the tail of the spin configuration with the initial. Okay, so maybe this is quiz. Okay. From this configuration of the icing model, which one has the lowest energy of the system? We have A, B, or C. Maybe this configuration 3 times T is, I think, is quite easily to predict. This one is has the lowest energy. Okay, but when we are dealing with some large classical icing model, this tutorial I will give you some the 30 times 30 side of the icing configuration. In the low temperature, the icing model predominantly with the ordered spin. This like this blue color represented by the spin up, and the orange color represented by the spin down. So you can see that in low temperature, magnetic material have the ordered spin. But when we are increasing the temperature of the system, so spin configuration have a mix up between a spin down, between spin up and spin down. You can see in here. So from low temperature to higher temperature have a transition between ordered and become the disordered phase transition. So we want to predict where this phase transition of the system represented by TC. And then, okay, this is fun enough. So we are dealing with two choice between ordered and also the disordered phase. So we could classify between two categories like this one. I give some example of the cat with the hands up and also the cats with the hands down. So this represented by the different category like binary classified. So when this P, the represented by the probability of the system have the categorized by the cat hands up, and then probability of the we got some measurement with the cat and categories in the hands down. So the next word or output of represented by the key class A represented by the cat hands up, and the key class B represented by hands down. So the loss of the learning we could define by like this. So this means that if your loss is minimal, if the QX, this means has matched the lapel between 1 0 or 0 1. Okay. Okay. The next back to this is machine learning representation. What about when we back to the physics? How to classify between the cat's spin, cat's hands on, heads up, and heads down. So we assume that okay, this 0 1s represented by the ordered system, okay, ordered system with low temperature, and then the cats with hands down represented by the higher temperature. We have we categorize by disordered system. Okay, we have two categories. And then after that, we have to collect between ordered and disordered with the binary classified. And then we have collect some data from the various data and using supervised learning. And then after learning of this some data, we construct, we can classify, oh, this system is ordered and this is ordered. And the final hands-on session, especially in the spin, classical spin, you could predict some the ordered spin and also disordered spin, and then mix in the between along with them. Okay. So okay, jump into another example. So after we discuss about the classical icing model, what about when we're dealing with some topological material? Schreiber-Heger model is a prominent, simple, non-interacting model exhibiting topological properties. So it was proposed to describe spinless fermionic, hopping on a one-dimension. This is one-dimension system. One-dimension lattice with a staggered hopping amplitude, like this represented by this. So this is Hamiltonian of the SSH model. This one is C and C Decker, represented by the creation and annihilation of the lattices in the set A, and V or W represented by the hopping parameter inside the unit cell and hopping parameter between the unit cell, like this, okay, respectively. So we can split some category of the SSH model become two, like this spin, ordered spin and disordered phase. Ordered phase and disordered phase. In the Schreiber-Heger model, so we could split become two categories of the topological properties, like a trivial phase represented by V is equal 1s and also W is equal 0, and we can reverse that topological phase is we setting then V is equal 0 and W is equal 1. Okay. So we are employing the same technique in the classical icing model, and then we are categorized by the system have the topological phase and also the trivial phase based on the based on the value of the V and W. After that, using the same technique, using supervised learning from the data we are create, after we can give some model that the system have a topological state and trivial state, but the arbitrary input data we are insert in the system model. Okay, so before we are going to jump into code, so this is SSH by human classification from the A and P. Which one is represented by the topological state and trivial state? Maybe I give you some little time, so please check. You can give some answer into chat. If you don't know what's going on, what categorized by this classify the A. So what's okay? Go A and figure A is represented by the topological phase, and B represented by a trivial space. Okay. So I think this the end of my brief explanation before we are going to jump into the code. So okay, I have need a little time to drink my water. Okay, so after a brief explanation about the system, we are going to jump into the code. Maybe it should be noted that for participant, the code I have submitted into my uploaded into my GitHub account. Please attention in the some announcement from the workshop admin. So please check again. Okay. Maybe. Okay. So. Okay. I think we jump into the icing spin configuration classification. So this workshop we want to predict some the transition temperature of the classical icing. Okay. Okay. Yes, of course. Dr. Sandi and also Dr. Sahu. Okay. So in this tutorial, we want to classify this one. I give you some notes that classify with ferromagnetic versus paramagnetic. So the data I have create have the Monte Carlo generic configuration of 30 times 30 square. So this is, I think this is very challenging to configuration a spin up, spin down represented by the by human to classify it, and then the data along with the icing data. So if you jump into my GitHub icing data, you can find some the data I have test and config and labeling between them. Okay, so we are try to import this one. So in this tutorial, we mix up between thoughts. You maybe you have sufficient with the another package about machine learning. I think it's one, but in this tutorial, I'll give you some delivers thoughts package. Okay. Okay, so okay, this one. Okay, when in the torch package, if you have a system that have installed some CUDA is like to accessing the GPU processing. but in my local computer, I have not installed CUDA. So when we running this code, you can find that is CUDA available false, but when false in your local computer under anything in the cluster, maybe this code running jump into your CPU. Okay, and then we try to access some data. I have a create in the icing data, and which one this we try to load of the training data, test and also like test data. And then what about the shape of the system? That system have the 1000 labels, and then different configuration, and 13. This mean that size of the icing. Okay. Okay, so the data should only take a value -1 and also +1, because this is represented by the classical icing model. This give some output on the spin up, on spin down. And then we are accessing from we tried in the data, I create some data from the T equal 1 Kelvin until 3.5 to understand the further data. Okay, what about when we are accessing the data? So we try to, maybe we want to see what happened. We are accessing the icing model with the temperature is equal to 1.66. This configuration of the system. So please remind that the blue colors is represented by a spin up, and orange color represented by a spin down. Okay, so this one is very interesting, because we want to not classify this is spin up and spin down, but we want to classify this system based on the transitional phase transition. So phase transition affected by temperature of the system. So we want to classify between two categories, like temperature in low temperature and also the high temperature. What is boundary between them? So we in here we try to, okay, T low I have defined 1.5 at the height to 5. So we are trying to labeling all of this data to represent by this. So when we have a T low, okay, back to labeling 0, and then T height with the 1. Okay, this one we try to labeling. So after have labeling of the data from your create, this is we want to plug into some new labeling, not only the spin up, spin down, but we want to labeling this one. Okay, this this temperature have the ordered phase, but this temperature have the disordered phase. Okay, so we would like to try again train the system, and the system maybe the save into the test data that's icing. So if you classify this test data and then training data. Okay, so the training data is saved into the previous folder. Which one? And then after that, the test data, we want to classify okay, after this one, we were to split of the training and test data. And then, okay, we want to print again. What's about the labeling? So we have the labeling of the system have the 600 between train X icing and also X icing for the test data. okay, this data have the same dimension. And what about when the how many data in only and train x1? So this one we only specific to access in the index one. Index one, this mean that there are some, I think you can see that 600 have the some data, but we want to try to put some disk, disk gitu. That's because this machine learning have a tensor representation. Okay, so representation they have a higher dimension of the not like a matrices, but the higher than matrix. So the 6, this means of only the labeling along with them represented by the temperature, and we want to try to access only the maybe T is equal 1 and when we pull it and we got some the temperature we got some data. The data have the 100 900. Okay, and then after we have training about the data, and then what we are to take our training and labeling the create a custom data set. So the data set we are say to maybe the data set is this some unique data you can access anytime when your simulation have done. So this one like save some model, and then some model you can maybe maybe the process another data. Okay, so we are try to mix up again some classifying some data, and then trying to data and also test the data. So after we have to pull into the maybe some room to have some data, and then we pass the argument to data loader to automatic patching, so sampling and shuffling and etc. So this means that maybe the after later on you want to have some another arbitrary input to classify this. My icing configuration is the ordered system and disordered system. You can find this very easily. Okay. Okay, and then what about this one is only check the data loader. We have the save. Okay. After we have save the our data into the data loader, this is a main setup of the machine learning. So this one I have defined some model with the RLU. With this mean that due to towards the 32 neuron hidden layer. So we have some 900 entries, because entries we have data have but in flattened and 30 by 13 configuration, and we have 32 neuron to hidden layer, and but we want to only to give two output. Okay, so two output, this mean that okay we have two output only. So two output, this mean that categorized by phase A and phase B, represented by the ordered phase and also disordered phase. Okay, so we are using from the some logical from the backward, and also the RLU activation function to doing this job. Okay. Okay, this one you can give some information how does machine learning doing the method. We are using linear in the feature 900 data and the feature 32 and base 2 when trying to employ some RLU, and then the feature from the linear combination in future that we are to output to one to maybe to looking for the only two. Okay. Out of that, we can trainable parameter give you some parameters. Okay, so we have done with the machine learning to learn from the data. So after we are doing from the data, we optimize the model. We are using a loss function optimization in this hand-on session. I define some cross entropy, but you can use the another entropy, say mean square error and anything else, and then optimize this tutorial. I will use the atom optimization, but you can use anything. Why do I choose this parameter? Because it's my perspective. This parameter give some error and loss information is low enough. Okay, and then to trying some this one. I only the train and also test data with the only learning with the 10 epoch. Epoch, this means how many we have the system I want to train, and then this you can see that accuracy of the learning by my code is with this one we have accuracy like this, and also averages of loss of the learning is represented by this. Okay, so I think maybe in this tutorial is enough. But if you want to try another method, but you can beat my accuracy, so please you can higher than epoch, and also try to and higher with the increasing of the page size, and so many technique, and also you can have some the technique to not only to learning not only linear RLU and linear from the neural network. You can beat my code, but another code. And then what happened when we try to what about our model to doing this job? So you can see that when the only I'll this machine learning, I'll give some only 10 epoch. So you can see that first learning is not fit again with the test data. So after a few epochs, test data and train data and test data have the I think as close enough. Okay, what about when we are dealing the interpretation and analysis of the icing? So I try to maybe, and we are to maybe some question in your head that how do we get the critical temperature from our neural network model? So this one is how is represented by the data loader have to you can save in your learning, and then we have a make prediction of the data. So in data, how many test data you have prediction in is from the icing test. You can follow, and then we try to collect some information with the temperature phase 1, phase 2, and also monetization, and then from this data we have the prediction of the machine learning through the neural network. You can see that the estimation transition from this icing model represented by this. So you can this one is ordered system, and this ordered system meet and maybe intersect between each other, and then we have find that the symptom data intersect in the around the 2.315. So this value maybe is we are compare with the exact thermodynamic limit is so this one. So I think that yeah, our results not bad considering it's only the finite size effect. So when you're dealing with the large large Ising model, so not only the 30 times 30 square, but maybe you can increasing until the infinite. So if you look again that above the label that we can see coincide between each other to represent by the phase transition in the learning of the monetization. So if you increasing of the icing to make precisely the transition dependent by the theory, this is a challenge enough because we want to define some large data, not only 30-30, but also maybe you can check with generate by Monte Carlo, maybe 100 and 100. But yes, if you hire there's some data, you have to maybe to find some another approach, not only in our tutorial, but you can increasing some the prediction to maybe the last epoch, and also the optimization you are use, not using maybe the cross entropy loss to find the some losses, and also the atom parameters. Okay. So, okay. Okay. So, I think any question? Oh, I think. Okay. Okay.
Oh, this room.
Oh, yes.
So
So any
there is a kind of comment in the chat box. In the chat box, they complain about the data set is showing some error. Can you confirm this?
oh, sorry. Your voice is maybe it's very low, I think.
Can you hear me now?
Okay, yes, I can hear you.
Okay, there is a kind of error they say. Can you check the chat box?
Okay.
They say that the data set is showing some error. Could you maybe confirm this?
Actually, yes. Showing some error because maybe we try to find some the using Monte Carlo. So this some errors occur when we maybe this one I'll give you some explanation that when we are dealing with the lower epoch, maybe some data I'll give you error. Error like this. Okay, there's learning not fit enough with the test data, and then you I think you could try something approach to make this data match between train and test data. So if your data is not matched in maybe okay. So I'll give you some suggestion. If you want to use this code to another system, maybe this not system not fit enough. So please because another system have a different approach to maybe the the learning, how to match this enough, because in machine learning we are dealing with the when we have some a few of a data. So a few of data, the accuracy may be lower than have your large data, but it should be not that in machine learning have the overfitting. So like this, you have some data and then a few of data, and then okay, maybe I'll give you a sort of explanation. You have a data, maybe this is one, okay, okay, this one, gitu. I think data is one, gitu. And then we are overfitting. This mean that your data give the linear regression, not only the covering of the data. This you have to very carefully about this data. So eventually we have to find some the plot the accuracy and loss of the system. Okay. Okay, so okay, how to implement icing machine learning using cascade? Okay, as far as I know that classical machine learning is better than the quantum machine learning. You can check the some tutorial of the, I think so, in this website. Okay, go to machine learning of this website. You can find the quantum neural network. So you can see Dr. Panrumuken. So this one is of how to dealing with the machine learning with the quantum computing. So we are to jump into the last. Okay, wait a second. Not this. Okay. Okay. Okay, the second. Okay, this one. Okay. So in as far as I know that in this tutorial I back to classical because quantum machine learning not good enough when we are compare with the classical. So if you follow this this data, so this data is only to train a data set of the maybe you want some people have to learn how to plot iris. Okay, iris data. This is very uh, maybe it's very interesting to learn from the basic of the machine learning to classify of this pedal and also the with that. So if you see that the result of the quantum machine learning and also the classical machine learning, that quantum classical learning have the higher the prediction rather than of the quantum machine learning, as far as I know. But okay, if you have any comment, you can interrupt me. So in a quantum machine learning, it's depend on the, maybe I could say that answers. This mean that how to define some the answers. This one when we trying to answers like the efficient SU2, we got some prediction higher enough when we are not doing it real amplitude. Okay. Okay. So can I continue my talk? Okay. So okay, we are going to a different example between among the icing. So the SSH models I have give you some explanation before in this slide. So in this slide, I'll give you how to create some data from the SSH model. So okay, maybe this one is very common. Okay, this one. Okay, so we want to extract some the eigenvalue and eigenvector from the SSH model, and then we can sort of the eigenvalue and also eigenvector. So this one is very it's interesting how to find some this data. So we create some data, and then we try to range of coefficient v and v and w, because we want to try to from the trivial phase become the topological phase. You can follow this. This training is data, and the number of unit cell. In this tutorial, I'll give you the egg, and then how many size of the v we can print it, and we want to sort the eigenvector and eigenvalue become from the lower eigenvalue to higher eigenvalue. Okay. So and then after create some data, you can see there, this is create some data, and then this section, what about how to labeling of the data? So in the topo, this represented by topological phase, and trivial represented by the phase. This topo is represented by 1 0 and trivial by 0 1. Okay, so this data sets is become 2. If you print enough, how many size data set we have to create? The data sets we have created is 10,000. Okay, so when we have data in configuration of 10,000, we want to maybe the 1/2 to become the labeling, become the topological phase, and then another one is a trivial phase. Okay, so we have now generate our data itself by yourself, and then okay, some data back to eigenvalue function. So eigenvalue function. So we want to plot the number of eigenvalue. This one we want to plot eigenvector only from the Hamiltonian in the on the system. So this one of the configuration. Okay, this plot up to the 1000 plot. Okay, this configuration we have create this one. Maybe the expert Dr. Sandy could represent by human. This is okay. This is topological. This is trivial. This is topological, and this is trivial. Anything. This is topological. So configuration of this one is a plot of between the set number. Set number, this mean of the configuration of the set number in the atom, and this is y function we want to plot. Okay, according from this data, we try to build some data set for the machine learning training as follow this one. Okay, the num Hamiltonian is represented by data set, because data set in this workshop in this hands-on session, if defined by the 10,000. Okay, and then the reveal data is true because we want to train again. The data can overlap each other. Okay, so this defined from, because the system size of the Hamiltonian as have the two power ends. So we want to this one. Okay, we try to make a creating data set of the system, and then after we have creating some data, we try to we want to load again to make some file PC3. This means that refers to validation set to give the some train data. After using some technique as before in the icing model, we want to save into data logger, and then training data set. After the training data set, we are doing the test data, and after we have a train data set and also a test data set, we want to making some find how many train and also test data we have create. So this one have the data we have grades only to 25 and to 256 data. Okay, so after we have some data and labeling of some data, we to make some we want to learning data become the input from the neural network. So if you follow this one, so if we have data this is saved, and then after 32, this mean of layer of the this neuron, so neuron learning, and then we try to Hamiltonian become 32. After that, you can set press to 32 to become 60, the double of the system, and we want to the end of the days, the result that I want to give some output only to like a phase topological and also a trivial phase. Okay, and then we have the same. Okay, then previous model we are using ADAM to optimization process. Okay, and this tutorial this section I will give another optimization. Okay, not using the ADAM optimization, but use stochastic gradient descent. Okay, so what happened when you have a different site? Okay, and then after we have optimization and calculate the some losses, we want to collect some the train data, loss, accuracy of the system, and then the same way we are to find epoch only the 10 from this workshop. You can enlarge with it, and we obtain that when the when the epoch after reach the 10, we got accuracy of my learnings give the 98. If you compare with the previous one, 96. So difference, I have mentioned before that difference accuracy of the machine learning to doing this job have a maybe different setup and also different definition of you optimization. Like this in the previous one, I employed them ADAM optimization, and but in the SSH model I employ the difference optimization, not using the ADAM optimization but the gradient descent. Okay, we want to plot what about my my code. So this one is very maybe you have a dealing with the machine learning. When your train data and test data have to fit enough, it's very okay. This your machine learning give some the good news for you. Then this is aha moment for me. Okay. So what about we want to plot the phase transition of the system. So in that topological phase, we are represented by the blue color. So I think maybe coincidence. Maybe the same with the maybe the same with the icing phase transition, like meet some point in the cross between the two different phase, like this one is a topological, maybe this one is topological state topo, and this one is a trivial. Okay, so but you know you don't conclude that okay, this I have you using this this number of set. Okay, we got some phase transition have the number this one accumulation. But if you want to clarify it, try to difference number of side, not only n equal x, but also in increasing of the number of side. Maybe you want to 12 and 6 to check the half probability of the system to create some compute the phase transition. Okay. Okay. So the end of the day, this is the last of this tutorial. Please, if maybe I think I have some enough time to doing the Q&A. So please, the participant, if you have any question, not only in this in today in this tutorial using machine learning, but you can ask me.
Hello.
Yes. Okay. Yes, that's it.
So in the chat box, I think there is one question that you haven't answered.
Yes.
About the way to extract the order parameter, for example, from icing model or the topological, how to get the order parameter.
How to get parameter of the icing model? Okay.
Yeah, for example, how to extract the order parameter.
Okay, so how to extract some the icing model? Maybe okay. This hands-on session I'll not maybe show you how to give you some code to how to create some the data. Maybe later on I'll give you in the GitHub. So please maybe stay tuned of the my GitHub account.
Any other question?
Okay, so maybe from the Anas Abdul Wahab. So this way to extract order parameter from the icing model. Okay, so I have answered. Okay, so I answer. Okay, sorry. Oh, this is the two question. Okay, so okay, the icing model maybe I have created before this workshop because the large enough to doing some the 30 site. Okay, 30 set of configuration with the various some temperature system, but in SSH model, you can maybe I think close enough. We have a bit of time this workshop to okay. I will give first how to create data in the SSH model, but in icing, okay, maybe I'll maybe with a back from the back, so to save our time. But in the SSH, okay, it's very easily to create it. Okay.
There's another question.
Yes.
Is it possible to do skirmion in quantum machine? Quantum machine learning.
The skirmion of quantum machine learning. Maybe I could answer that I don't know how to dealing with the skirmion quantum machine learning. But if you maybe if you have some data, you can this workshop you can classify between two categories, like represented by the binary classifying. Like okay, maybe I don't know how skirmion. I don't know how to skirmion thing with it. Maybe you want to compute some phase transition. Maybe in the skirmion have two ordered, like the SSH model have the topological and also the trivial, and the icing have the ordered and disordered system spin configuration. Sorry, but in skirmion maybe I don't have any idea how to dealing with it. Okay, I'm sorry.
Ada question from the audience who wants to ask directly. Maybe somebody wants to ask directly by raising the hand.
Okay, so.
Okay, there is another question in the chat box about SSH
Okay.
folder.
Oh, so maybe you can create the SSS model in this tutorial, because I have to find before these tutorials. So in the machine learning SSS model you can create by you. Okay, so not because this code in my Discord I forgot to when we are not to find some the folder you can create automatically. Okay.
And there is another question about the difference between these two models. Oh, maybe this one first. There is somebody raising hands.
Okay.
From Mr. Mrinal Kanti Kiri, can you unmute?
Hello.
And just
Hello.
Yes. Hello.
Yes.
Hello.
I just want to know two things. First, like in circuit, quantum circuit, in previous day training, you talk about the quantum circuit. So
Okay.
I'm just curious to know about if there is a large depth quantum circuit, can you do make it a short depth or constant depth quantum circuit using machine learning? Or if it is yes, then can you give some intuitive idea how one can do it?
Okay, so okay, thank you, Mr. Marinal Kantikiri. So as far as I know that okay, the classical machine learning have maybe the best to predict some the system, anything else. So what about the quantum machine learning? Quantum machine learning have some the dependency of the classifying about the system, like what about we are dealing with our system, and then what about answers I have mentioned before that we want to create maybe I can clicking some answers. So we are dealing with the different answers have a different accuracy. So yeah, maybe I have explained it before what is different between them. So please carefully that not only in the classical is also have the low accuracy of the predicate sum the system. So because I have you maybe I show you this one is a very okay. This is one okay, sorry. This one is very different. In the icing, in the classical machine learning, this one, okay, when I try to using the atom optimization, okay, we can compute with the same epoch with the SS model, have it accuracy up to the 96. Say, what about the SSH with the difference optimization? So different optimization in the SSH touch into the 98. So in the classical machine learning, different optimization, different system, and the different data we have trained, and also the number of epoch. So effect of the accuracy of the system in the quantum machine learning, but in the in the classical machine learning, but in the quantum machine learning, we are dealing another some the categories, not only of the like this classical machine learning, we are dealing with the answers. So if you jump into this URL, the website, this Cascade Machine Learning, you can see that SVC, this means that of the to find some the classical machine learning, and the feature of this is very high. So until this when we are using the quantum machine learning, we are dealing with the, I could say this is answers with different answers, real amplitude, and also efficient SU2 kit have a difference difference accuracy. So yes, in this author, I'll give it expressingly that and give some emphasize that classical model perform better than their quantum counterpart. But a classical has a long way, and quantum is okay level of maturity. Okay, so this one you can choose. You can choose your perspective. You want to learn, but if you pit the classical machine learning through the quantum machine learning, I think it's good enough to study.
Thank you for your answer, but there is also another question here in the chat box. If
Okay.
I'm a beginner, what should I do to start learning this?
Okay, if you begin of the quantum machine learning using quantum computing and quantum machine learning, please maybe the basic of the quantum mechanic you have to understand first. So become okay. So I think it's the tool like a Qiskit and also PyTorch give you some help to push off your study, but the basic of the quantum machine learning, and also the classical machine learning, and then the quantum computing is very first to study, because my experience before that when we are to jump into the through the coding like the Qiskit, maybe is the first my experience. I have a whole of the knowledge of the quantum computing, like how to. I have the same when we are dealing. Sorry, we are dealing this ones. We have okay, it's Hadamard, like Hadamard. You can in your computer, you can define some the unitary matrices, can compute like, okay, this one is result. But you are dealing this one, what does definition of this? Okay. So in the case kit, okay, I'll give you some number. But then what does meaning of the Hadamard kits in keep it 1 and keep it 2? What is that's meaning? So that's meaning that in the mathematical operation, you have some operation chronicle products between Hadamard kits and Hadamard kits. So this is a basic to have to learn. And what does meaning of the supervised learning, unsupervised learning, and decision tree, and also that etc. Along with the classical machine learning. This is very first to have to you want to study, jump into the coding. Okay.
So another tips for the beginner is to download Mr. Yusro tutorial from GitHub.
Yes, this is a very short. But in my tutorial is I think is not beginner, I think so. Maybe okay, maybe I'm looking for some study to we want to from the basic. I think I'll give you in the Discord channel. Okay.
And there is another question about, is it possible to use quantum machine learning to study Hamiltonian dynamics?
Okay, so to study Hamiltonian because I okay, so maybe maybe nowadays I could say yes, because I'm not expertise in this area. Maybe Dr. Citra in this also in the keynote session of the keynote session and this event have some knowledge about that. So maybe I could say that I don't know, maybe in this today, maybe the someday I have to learn, okay, this is one, okay, that I can easily to understand it. So I'm sorry.
Okay, we can discuss with the first speaker of today's session.
Yes,
right?
Yeah, okay. Yes, this is for second.
And another question is about, if I have time series data, many snapshots, which machine learning model should I use?
You have some series model, okay? Oh, which
data?
Oh, time series data, okay.
Which model should I use?
What about the same model you have used? Maybe okay, this is I have implement this time series data to predict stock market, I think. Stock market. So this is okay. I apply the some machine learning to predict some stock market in Indonesia. So we have the time series. So dealing with the time series is challenge enough, because we have to deal with some large time series, and then when we are dealing with a few data, because the time series have to predict some previous data and also to try to predict the future one. So as from my experience, supervised learning is appropriate of this study from the time series. From my experience, okay.
And also, I think in Discord channel, there are many participant complaints that there are some errors in the installation. Can you maybe confirm this in a Discord channel?
Okay.
About the installations, there are some errors.
Okay.
Can you show the installation directly?
Okay, so a second. Try to. Okay. So let's complain about maybe from the Mrs. Sakine about how to dealing with the Jupyter Lab in the inside of. Okay, so I'll give you wait a second. Back to my works. Okay. 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 So try to. If you have any. Okay. So there are so many error in your local computer. Please in this workshop I try to with using some terminal from the Ubuntu. Okay, sorry, to dealing with this. Okay, so hang on a second. Okay, okay. So okay, the first one is from the in my hands-on session to dealing with this one. You try to first conda create main minus n QML CMP. We want to specify in using the Python 3.4. You can check enter. This is going to install the virtual environment in your local computer. Okay, so after you have installed this one, okay, you can check. I don't know how to specify of the, maybe you can. Okay, so maybe you have a like my style have so many virtual environment of my local computer, but okay, this one I want to access QML CMP, so you can activate first conda activate QML CMP. Okay, and then you could install first like okay, I want to, and then the Discord in hands-on session one. I say gonna trouble but installing Jupyter Lab. You can pipe install and direct to in the environment QML CMP. You can Jupyter Lab this one. Okay, so hang on a sec. Wait a second. Is try to install of the system. Okay, this is done. How to call the Jupyter Lab in your local computer. So when you're dealing, you can type the Jupyter Lab, but because in my laptop I use the Linux subsystem. So when we are try to directly to find some like this Jupyter Lab, it gets I'll give some error. So we can use the no browser. Okay, no browser. This means that you have to not show the Jupyter Lab into your local point computer, but you can click one of this link. You can click with the control and mouse and direct to up to the local your local computer. Okay. Okay. Oh, so hang on a second. So wait a second. This is error how to install this previous. Okay. So indirectly you could use the install some the package. Maybe we want the install the first package, like okay, this one, this Qiskit, the session day 1. You can copy in the Jupyter Lab. How to access this Jupyter Lab? You can choose of the Python 3. You can choose there's the Jupyter Lab logo. You can copy this, and when you install this is the cell of the Jupyter Lab, don't forget to add the apostrophe. Yes, this is one very very important. But when you install this one is a very, I think this is enough to doing so. Okay, but okay, if you ever face some error again and many error, and then maybe your laptop and your PC have support, you can, I have mentioned in my GitHub, you can try to Google Collapse. But when the Google Collapse have a restriction in your area, so I think one of them is you to try to install any your local computer. Okay.
There is another question in the chat. Interesting question here about how to detect that our model is overfitted.
Sorry. Detect what?
You're still about the overfitting of a model. How to detect
Yes.
if our model is overfitted.
Okay. This is this our model is overfitting or not. This is very yes. Yes, this is a sophisticated study to how to detect of this model of the overfitting or not, because maybe you can check. Okay, and okay, maybe I'll give some suggestion. If you face if you have some if you have a few data to learn from the machine learning, maybe the possible the overfitting is for the immerse of the system. But also, if you have a large enough of the system, large of the data, but the data is the bad. I think this mean the bad is this. If the spread of the data is very very high, like this, okay, so maybe I'll okay, I noted. Okay, if you have a okay, the machine learning enthusiasm, the very happy with we have a data is very so very good and very structured. But when we are dealing with the data is very very bad, I think you know what does meaning of very bad of data. If you have data, some maybe this is some indexes. We are try maybe okay. I think enough when we are dealing with the stock market. Okay. Okay, we are dealing with the stock market. Okay. when we have data like spread like this, like this, like this, like this, like this, like this, how to give some the regression of the system. This one, or this one. Okay. The possible of the difference fitting the data depend of the your style of data. So if you maybe you can check first what your data or your data maybe not clean enough. So maybe the overfitting comes to the data is not clear enough. I think that there are so many noises, so many unlabeling, and then so many difference like this. You can maybe the overfittings of the system emerge. But if you have the some data like this, okay, you can maybe the clustering this data, maybe have some a different result of your data.
Is there any mathematical calculation about overfitting? Mathematical quantity to like formula.
Okay.
It's larger
maybe
than this. It is overfitted.
Oh yes. Okay. So maybe I forgot I have read some book, but how to defend this model of overfitting or not. Maybe if I have maybe when I found this characterized, I'll give you in the chat box, in the Discord channel in the hand-on session day 2.
There is no more question here. Yes. I don't think we have any other question. And the time is almost finished. So shall we close this hands-on session? Okay. So thank you for your wonderful teaching for the past 2 days. Useful.
Okay, thank you, Dr. Sophie.
And I think everyone is happy with your teaching. So let us give him an applause. Okay, I'll give you an applause.
Thank you.
Okay, let us welcome back Dr. Ahmad Nugrah.
Yes, thank you very much.
So for the closing session.
Right. Can you hear my voice?
Yes.
Yes. Okay.
Right. So this moment. Okay, now hopefully you can see my screen. Good evening from my place. So it's already 7:30 here, 7:30 p.m. in the evening. And also good afternoon in the CEST, Central European Summer Time. Good morning in some other places. So good, good anything, everyone, our colleagues and also distinguished speakers, as well as all of the participants of this workshop. And maybe I would like to introduce myself again, although in the beginning of this workshop, I've introduced myself. So I'm Nugraha, the chair of this workshop. It's now kind of session for closing remarks. But yeah, don't worry, I will not take much of your time. Actually, now we have saved much of our time because one speaker did not come, unfortunately. I've actually already called her through Discord and also I also sent some reminders through the email, but no reply, unfortunately. So it's okay, I think. Eventually, we could make all the sessions except that one. And on behalf of all the organizers and ICTP Secretariat, we would like also to say thanks a lot for all of your patience, participation, and contribution to this workshop. We also apologize for any inconvenience or technical problems that you may have faced during the workshop. I hope such problems do not make you
unhappy. And yeah, eventually we could proceed the workshop up to this stage. But I think this is not, this is actually not the real end of the workshop. For some of us, it might be the beginning of knowing each other. And yeah, the 3-day workshop should not be the same as a full-time school. As the organizer, we actually think of this workshop more as a kind of platform to grow your collaboration networks. Not only do we learn something new that could be our future expertise, but I guess we also have shared some context each other, email and so on. And even for myself, although I did not give any scientific presentation and I did not give further details about myself, I was mostly silent in this workshop. I was quite surprised to get some social media invitation, for example, in LinkedIn and others. So it's very good sign that this workshop can grow the collaboration networks between all of us. And yeah, now some important information after this workshop, and maybe you are waiting for this. We suggest you to check regularly 3 main places. First one is your own mailbox. So please also check spam folder. We are just afraid that some information from the ICTP Secretariat enter your spam box, because some of the questions in the Zoom chat or in the Discord server actually had some answers in the email, in the explanation from the ICTP Secretariat. And the second place that you should check regularly is also the events website. This website. So we have created the QR code for that, for this event. And following the ICTP standard, actually all the slides, materials, and recordings would be available there. But we will check again the confidentiality from each presenter and also the contributed speakers. And last one, please also join Discord server. And I guess more than 50% of the participants already joined that. I checked that it's the members of the server is already around 300 participants from the registered almost 400 participants. So, but yeah, for some of us, it may be annoying to get message or to be mentioned in the server. So we will make the server in the slow mode from next week, and also it can be archived. That means that after we think there is no problem anymore from all the participants and all the curiosity or questions are answered clearly, so we will archive the server, which means, yeah, you cannot send a message anymore, but you can still read and be the member of this server and check some materials, some slides, some question and answer that have been archived there. So I will show you some example here. Maybe some of you might not be familiar yet. For example, in Keynote 1, here Prof. Ming Dali was one of the most active speakers to chat in the Discord. So you can check here the abstract, but the abstract is also available from the ICTP website, this events website. And from here, you have some questions. And yeah, Prof. Mingda, when he has available time, he answered the question nicely. And he also already shared the PDF file of his presentation, and it's pinned. You can find the important, important messages here. So we pinned the abstract and also the slides of his presentation. And then, yeah, you can follow some discussion here, some question and answer, which were not discussed in the Zoom meeting, but yeah, somebody had questions posted, and then they asked directly in the Discord server. And also for the hands-on session, we have 2 hands-on sessions here. For the hands-on one, it was yesterday, and then hands-on 2, yeah, it's today. Here the tutor already gave the link how to obtain the files, Jupyter notebooks, the datasets, and so on. So you just need to access the GitHub repository, click there, and download all the files. And even if you are already familiar with Git system, Git command, you can clone the repository and then check if there is any update from the tutor. And what else? Yeah, some contributed speakers were also quite active, and I was very happy actually today, although we did not have the last contributed talk. Professor Flavia here already kindly answered some questions from the participants, and Dr. Dominic also answered the questions here. So yeah, feel free to discuss with each other in the Discord server, but please be kind and keep the manner, scientific manner. Do not rush to get the answer from the speaker. We should admit that yeah, we should recognize most of them are busy. Most of them are professors and doctors, so they have their own research. So that's why we think that it's good to make the Discord server in the slow mode from next week. And the recordings, slides, or other resources, again, as long as they are not confidential, will be shared to the participants. So don't worry, we will give this information, but please allow us to wrap up the materials for a couple of days. Hopefully within 1 or yeah, at most 2 weeks, we can inform all of you through the ICTP email, ICTP Secretariat email. And some of you already also asked about the certificates. This was explained in the beginning of the workshop and also explained in the email in the Discord server, but I just mentioned here once again. The certificates will be given to those who attended the Zoom meeting more than 50%. So that's why we use not only for security, but also for analyzing statistics. We use the Zoom personalized links that made it possible for the ICTP Secretariat to confirm how many hours you attended this Zoom meeting. So we had, by excluding the break, we had totally 12 hours because 4 hours times 3. So then we are expecting that those who attended the Zoom meeting more than 6 hours will obtain the certificates. And yeah, if you need to join more advanced courses or more beginner courses, you can always see the ICTP website and check the events, the agendas from the ICTP calendar. But yeah, in relation with our own research center here at BRIN, at National Research and Innovation Agency in Indonesia, if you ask us, will we make this workshop again? Our answer is yes, hopefully, because 2025 is the International Year of Quantum Science and Technology. So we really hope to make another kind of this workshop with a similar format and theme. But yeah, we are very sorry for any inconvenience due to maybe we are just beginner in making this kind of workshop online with many participants. So we are also sorry for not satisfying all the participants with different backgrounds. For example, I just watched some comment that some presentations were not condensed matter physics, were not quantum computing, were not something. But yeah, we combine everything actually. So then we should not expect that everything will really match to your specialized background. So then in the next workshop, we might organize a more beginner-friendly workshop separately from the specialized or expert one. So yeah, maybe probably some of you also have impression that the participants of the current workshop are too mixed from complete beginners to very advanced. So then yeah, we will consider to make this separation. But yeah, if you have some suggestions, or even we can collaborate with different institutions in the world to make this kind of online workshop and suggest some specific themes or speakers. So please drop a message and send us an email at quantum@brim.go.id. So this is our official mail. Hopefully you can give us suggestions for this future workshop. And some of you also asked about the collaboration opportunity. Oh yeah, let me check this meeting chat also. Yeah, you can check researchers or people on our website. And again, we should declare that we are complete beginners, not really beginners, but yeah, kind of beginners in the quantum research. So do not expect too much, but we really appreciate any collaboration with any professors, researchers in the world, especially for us in the global south, in which the resources and opportunities are not so much compared to the developed countries. So then we really appreciate if you can collaborate with some of our researchers. You can check the people on our website, quantumresearch.id, and our research fields are quite broad, from condensed matter physics to particle physics and anything involving quantum physics. we do such a research. And also, please, it should be noted, we are not ICTP, but we are having cooperation with ICTP in making this workshop for this year. So hopefully, next year we can make collaboration or cooperation again with ICTP for this workshop. Even if it's not possible in the next year with ICTP, we are still considering to make this kind of workshop by our institute or by collaboration with any of you. And I think that's all, and hopefully we can still make contact each other through email, through Discord, and through other social media. And yeah, lastly, once again, we should acknowledge great effort and support guidance from the ICTP Secretariat, especially Miss Victoria Lovova, who is the person in charge to send you all the information through the email, and also Mr. Hasan Ali, and some others behind the scene, the Zoom operator, and so on. And we really thank to our staff at Brain Research Center for Quantum Physics, Dr. Sasvan and friends, so many friends now in our room, making this workshop possible for all of us. And also from our advisors at Institute of Technology Bandung and University of Indonesia. And last but not least, we are very grateful to all the speakers, Prof. Ming Dali from MIT, Prof. Khairul Anwar from Telkom University, Prof. Andrian from ITB. He has got sick yesterday, so we were very sorry that he did not present by direct presentation, but by using video. However, we were very happy that he still could answer some of your questions directly in the Zoom meeting. So hopefully he can recover very soon and answer your remaining questions in the Discord server. And last keynote speaker was Dr. Cica Agustiani from Sorbonne. So she also made a very nice presentation, and we learned a lot, and hopefully she could answer also some remaining questions in the Discord server. And of course, all the contributed speakers, some of them are professors and doctors and students, 10-1. Eventually, we could make these contributed speakers presenting their work in this workshop. And yeah, of course, all active participants who have joined this workshop from the beginning till the end, we thank you so much. We are very happy that you can join this workshop, and hopefully we can meet you, we can see you again in the upcoming workshop in next year, upcoming years, and yeah, in the future. I think that's all from me, and if possible, if you can open your camera, we would like to take the final group photo. So then, yeah, we can make a good memory, and it will be put on the ICTP events website as well. Okay. Wow, now 100 chats. Sorry if I could not answer all your comments in the Zoom chat. Yeah, while waiting for everyone to open the camera, maybe I just comment some of your questions about WhatsApp group. I think, yeah, we apologize that it's not really safe to make a WhatsApp group because we share to personal contacts by the phone number. So I think it's better to use Discord. So that's actually the reason why we use Discord also for security. And then for the certificate, when I did not mention in the slides. We expect that the certificate will be sent to you for a couple of days because the ICTP Secretariat should analyze your statistics of attendance. But hopefully within 1 or 2 weeks, it will be sent to your email address. So don't worry, please just keep waiting and little bit be patient for that. The ICTP Secretariat will send you the certificate. Okay, so now everyone is already opening the camera. And I think the organizer can be ready for taking, at least there are 3 slides right now. Who open the camera? Can we start from the first slide? 3, 2, 1. Let's take the screenshot. And then second slide. Third slide. Oh, now there are 4. Okay, then 4, final one. Okay, so I think that's all for this time. We actually finished really on time because it's now 7. Now in the CET it's 2:46 p.m. If we do not consider the 15 minutes from the absence of the contributed speaker, the last speaker, so we made it on time. So enjoy your day for the one who just started morning, and then good evening, good afternoon, good evening for other places. Hopefully we can enjoy our weekend. So it's now going to be weekend in my place in Indonesia. So see you, and the organizer will stop the meeting by ending this session for all. Thank you very much. Thanks again. Bye-bye.
And meeting?